For as long as humanity has looked up at the stars, we have imagined a force so vast and unending that it could power every dream we've ever had. An energy so pure, so boundless, that the limitations of our modern world, scarcity, pollution, and dependency, would dissolve into history. Through the ages, we've chased this vision. Coal sparked the Industrial Revolution. Oil fueled empires and global trade. Wind and solar whispered promises of renewal. Nuclear fission showed us the staggering potential hidden within atoms. But each of these steps, though transformative, was still incomplete. The dream of infinite energy, the true unlocking of the universe's power, remained out of reach. And yet today, the frontier of science trembles with possibility. After centuries of burning, digging, and refining, researchers now stand on the edge of a discovery that could redefine civilization itself. Imagine an Earth where energy is as abundant as air, where cities glow without cost, and where human progress is no longer measured by what we consume, but by what we create. The question that once seemed like fantasy, can we achieve infinite energy, has evolved into a scientific pursuit filled with real data, real laboratories, and real hope. Energy is the invisible current that sustains everything. It illuminates our homes, propels our transport, drives our industries, and binds together the digital networks that shape modern life. Our societies are built on it, our economies depend on it, and our futures will be defined by how we produce it. Yet, for all our ingenuity, the sources we've relied on, coal, oil, natural gas, and uranium, are bound by finitude. They run out, they pollute, they divide nations and poison ecosystems. The race to find a clean, infinite alternative is not just scientific, it's existential. The concept of infinite energy refers to an inexhaustible power supply that can be sustained indefinitely without consuming or degrading the planet's resources. It's the idea that energy could be produced continuously, cleanly, and universally, available to all people at all times. It would not fade with time, depend on weather, or deplete the earth. Theoretically, it could support the growing demands of humanity forever. To grasp its magnitude, consider the limitations of what we use now. Fossil fuels, coal, oil, and gas, are the compressed remnants of ancient life. They took millions of years to form beneath immense pressure and heat, yet we burn through them in mere centuries. When they are gone forever. Nuclear fission provides enormous power but carries risks. Radioactive waste, accidents, and political tension over weaponization. Renewable sources like wind and solar are cleaner, yet intermittent. Night falls, the wind stills. Storage remains costly and imperfect. Infinite energy, however, represents the ultimate shift. Instead of extracting or burning fuel, we would learn to harness natural processes that never end. Perhaps the fusion of atomic nuclei, the same reaction that powers the sun. Fusion promises unimaginable efficiency. Small amounts of hydrogen could yield more energy than tons of coal without producing carbon dioxide or long-lived waste. Theoretically, it could run for as long as the universe exists. Scientists have spent decades chasing this reaction, working to recreate a miniature sun contained within magnetic fields on Earth. This pursuit has inspired projects across the globe. In southern France, the ITER experiment is building the world's largest fusion reactor, aiming to prove that more energy can be produced than consumed. In the United States, the National Ignition Facility has achieved milestones where bursts of laser energy momentarily reach ignition conditions, tiny flashes of what could become the future of power. Private companies, too, have entered the race, experimenting with compact reactors, magnetic confinement, and advanced plasma control. Every discovery brings humanity closer to mastering a process once thought impossible. But infinite energy isn't only about physics, it's about transformation. The consequences of achieving it would ripple through every layer of human existence. No longer would energy scarcity dictate geopolitics or wealth. Oil wars would fade into memory. Economies could flourish without environmental debt. Deserts could bloom with desalinated water. Cities could operate with zero emissions, and humanity could, for the first time, live sustainably within its planetary boundaries. The environmental implications are profound. Fossil fuel combustion remains the largest contributor to climate change, releasing vast amounts of carbon dioxide and methane. These gases trap heat, driving rising global temperatures, melting ice caps, and disrupting ecosystems. If infinite energy became real, the dependence on such fuels would vanish, the air would clear, oceans could recover, the delicate balance of Earth's climate might finally stabilize. Yet, the pursuit of infinite energy also raises deep ethical and philosophical questions. If power becomes truly limitless, how will humanity wield it? Will we use it to heal the planet or exploit it further? History reminds us that technological revolutions always bring unintended consequences. Infinite energy could end poverty and scarcity, or if mishandled, intensify inequality by placing control of limitless power in the hands of a few. Still, the potential remains too great to ignore. In many parts of the world, billions still live without stable electricity. Hospitals rely on unreliable generators, schools go dark after sunset, and communities remain trapped in cycles of poverty because they lack something as fundamental as power. Infinite energy could break those chains. A single compact reactor, for instance, could supply clean energy to entire regions, transforming education, healthcare, and industry. Humanity's journey toward infinite energy is more than scientific. It is a story of persistence, imagination, and defiance against limitation itself. From the first spark of fire to the hum of fusion plasma, our species has been driven by one unyielding question. How do we harness the universe's forces to survive, to thrive, and to endure? And perhaps somewhere deep in a laboratory, beneath magnets humming like stars and plasma swirling like miniature suns, that answer is beginning to form. And so the prospect of infinite energy emerges not just as a scientific dream, but as a force capable of reshaping civilization itself. Imagine a world no longer bound by scarcity, a world where power flows endlessly, cleanly, and freely. The implications would be nothing short of revolutionary. Nations that once struggled with the economic and political weight of energy dependence could finally stand on their own. For centuries, energy has defined the hierarchy of power on Earth. It has drawn borders, fueled wars, and built empires. But infinite energy could dissolve that hierarchy entirely. No longer would a country's prosperity depend on the luck of geography or the presence of fossil reserves buried deep beneath its soil. Energy independence would transform global economics. Today, fluctuating oil prices and volatile gas markets dictate the cost of living for billions. When electricity rates surge, industries hesitate, families tighten budgets, and governments scramble to stabilize economies. But if energy became virtually free, the entire foundation of modern economics would shift. Homes could light up without concern for bills. Cars could glide silently across continents, powered by an inexhaustible current. Factories could run day and night, not out of necessity, but out of limitless possibility. Such a change would ripple far beyond wallets and balance sheets. Governments that currently spend billions importing oil and gas could redirect that wealth toward progress, healthcare, education, infrastructure, and innovation. The burden of fuel subsidies could vanish, replaced by investments in science and welfare. A stable, self-sufficient energy system would anchor societies in newfound security. And as costs drop, creativity would rise. The technological consequences of infinite energy are almost impossible to overstate. Consider the industries held back today by energy constraints. Space exploration, for instance, could evolve from a daring experiment to an everyday enterprise. Rockets could launch not once or twice a year, but as frequently as cargo ships cross oceans. Permanent bases on the Moon or Mars would no longer be fantasy. They could become stepping stones to a solar civilization. Deep space probes could travel across light years, powered indefinitely by the boundless energy we once thought belonged only to stars. Back on Earth, this abundance could redefine progress itself. Artificial intelligence, once limited by the cost of massive data centers, could process information on scales unimaginable today. Manufacturing could become cleaner, faster, and more efficient. Medical researchers could run complex simulations non-stop, accelerating discoveries that might cure diseases once deemed incurable. In transportation, fleets of electric vehicles could dominate every road, every ocean, and every sky. The fossil fuel era would fade into history, an age remembered for its ingenuity, but also for its cost to the planet. Infinite energy, however, is more than a technological question. It is a moral and environmental one. Fossil fuels have powered humanity's rise, but at immense expense. The carbon dioxide they release traps heat in the atmosphere, distorting climates and ecosystems. Air pollution from burning coal and oil cuts millions of lives short each year. Even worse, these fuels are unevenly distributed, creating geopolitical rivalries that have shaped global politics for generations. Oil-rich nations hold sway over those that depend on imports, and every fluctuation in energy supply ripples across the planet. Infinite energy would end that imbalance, giving every nation equal access to power, literally and politically. But achieving such a dream is no simple feat. Scientists are pursuing several paths toward what could be described as the closest thing to infinite power. The most famous of these is nuclear fusion, the same process that fuels the sun. In the heart of our star, hydrogen atoms collide and merge into helium, releasing energy that sustains all life on Earth. If humanity could harness that reaction safely and sustainably, we could replicate the sun's brilliance here on our planet. Fusion reactors are already being tested in laboratories around the world. Each breakthrough brings us closer to the moment when the energy that powers the cosmos becomes part of our daily lives. Yet the challenge remains immense. Fusion demands temperatures hotter than the sun's core and pressures that are difficult to control. Still, the reward would be unparalleled: clean, stable, and nearly limitless energy drawn from the most abundant element in the universe. Other renewable sources also point toward the same dream. Geothermal power taps into the Earth's inner heat, a steady pulse of energy generated by the planet itself. In places like Iceland, geothermal systems already power entire cities, offering a glimpse of what long-term sustainability looks like. Though not truly infinite, geothermal energy is so enduring that it could last for thousands of years without depletion. Solar energy, too, stands as one of humanity's greatest opportunities. Every second, the sun releases enough energy to power human civilization many times over. Modern solar panels convert only a fraction of that, but technological progress continues to push those limits higher. With improved storage and transmission, solar power could soon provide a near-endless flow of electricity. As long as the sun burns, which will be for billions of years, solar energy remains effectively infinite. There are even more speculative ideas. Some physicists imagine harnessing the rotational energy of black holes, where gravity twists space and time into extremes. Others propose tapping into quantum fluctuations, the tiny bursts of energy that arise spontaneously in the vacuum of space. Some go further, suggesting that dark matter or dark energy, the mysterious forces that shape most of the universe, might one day be used to generate unimaginable power. These theories dwell at the edge of known science, but they remind us of a fundamental truth: the universe is full of energy. Our challenge lies not in finding it, but in learning to use it wisely. To understand why infinite energy is so compelling, one must first grasp the nature of the finite. Fossil fuels, coal, oil, and natural gas, are products of ancient life. Over millions of years, heat and pressure transformed organic matter buried deep within the earth into concentrated energy sources. Humanity's industrial rise depended on these fuels, but their supply is limited. Once burned, they are gone. It would take another span of millions of years to recreate what we consume in mere centuries. They have given us progress, but also pollution, inequality, and conflict. Infinite energy represents the opposite. It is power that endures beyond human timescales. It draws from sources that renew themselves: solar radiation, wind currents, ocean tides, or planetary heat. These are natural processes that continue whether we use them or not. They offer not only continuity, but balance. By shifting to such sources, humanity could align its survival with the rhythms of nature rather than against them. And so, the pursuit of infinite energy is more than a technological ambition. It is a statement about what kind of species we wish to be. A species that burns through its inheritance, or one that learns to sustain itself in harmony with the universe. From the depths of the Earth's core to the heart of the sun, the energy is there, waiting. Whether through fusion, geothermal currents, solar radiation, or theories not yet proven, the quest continues. If humanity succeeds, it will not simply change how we power our machines. It will redefine what it means to live, create, and explore without limits. Furthermore, extracting and burning fossil fuels brings a heavy burden upon the planet. Each barrel of oil pulled from the ground carries the potential for disaster. Oil spills that blacken oceans, suffocate marine life, and poison coastlines for years. Every ton of coal burned releases soot and toxic gases that choke the air, staining skies gray and feeding the rising tide of global warming. Forests fall to make way for extraction sites. Habitats disappear, species vanish. The cost of this energy, once considered the backbone of modern civilization, grows harder to justify with each passing decade. Experts have long warned that the age of easy oil is ending. The reserves of coal and natural gas we have relied upon for centuries are finite, shrinking under the weight of our demand. As the wells run deeper and the mines dig farther, the effort and expense to extract what remains increase. Yet, even as the price of access climbs, the invisible debt we owe to the earth rises faster. Air pollution thickens, oceans warm, climate systems grow unstable. Each barrel, each spark accelerates the damage. This is why many scientists and environmental leaders agree on one crucial truth. The future depends on shifting to sustainable, infinite energy sources. Unlike fossil fuels, these sources do not face depletion. They draw their strength from natural, ongoing processes, sunlight, wind, and water, forces that have shaped the Earth since long before humanity existed. They are not merely alternatives, they are successors. Take solar power. The sun is a nuclear furnace suspended in space, releasing a staggering flood of energy every second. To grasp its scale, in just 1 hour, the sunlight reaching Earth contains more energy than humanity uses in an entire year. It is as if the planet lives beneath a constant downpour of power, a gift that we are only beginning to capture effectively. Solar panels, covered in photovoltaic cells, are our instruments for harvesting this light. When sunlight strikes these cells, it excites electrons, creating an electrical current. This direct conversion of light into electricity is clean, quiet, and instantaneous. As long as the sun continues to rise, which it will for billions of years, solar energy remains available. Regions bathed in sunlight can power homes, cities, and industries without burning a single drop of fuel. But solar energy's promise does not come without limits. Clouds, nightfall, and seasonal changes all affect output. The challenge lies in storage, how to keep the power of the day alive through the night. Engineers are developing advanced batteries and thermal systems capable of storing excess energy, ensuring a constant supply even when the sky goes dark. Each improvement in storage technology brings the solar dream closer to full reality. Wind power tells a different, but equally powerful story. The movement of air across the Earth, shaped by differences in temperature and pressure, has been a part of our planet's rhythm since its formation. Wherever wind flows, it carries kinetic energy waiting to be captured. Tall, slender turbines rise from coastlines and plains, their blades sweeping through the air like silent sentinels. As the wind turns them, they generate electricity through motion, translating nature's breath into human power. Wind farms, collections of dozens or even hundreds of turbines, can now supply electricity to entire regions. They operate without smoke, without waste, and without the carbon legacy of fossil fuels. From the blustery shores of Denmark to the wide prairies of North America, wind energy has become a cornerstone of renewable progress. It is adaptable, too. Small turbines can power remote villages, while massive offshore installations can feed megacities. Yet, as with all technology, challenges exist. Calm days reduce output. The placement of turbines requires careful planning to minimize harm to wildlife, particularly birds and bats. Still, studies consistently show that the environmental footprint of wind energy is minor compared to the devastation caused by fossil extraction. In balance, the wind remains one of our cleanest and most reliable allies. Then there is hydroelectric power, the harnessing of moving water. For as long as rivers have flowed, humans have sought to capture their force. Modern hydroelectric plants do this on a vast scale, converting the kinetic energy of flowing or falling water into mechanical motion that drives generators. Dams and reservoirs store immense quantities of water, releasing it through turbines to produce continuous electricity. This method is remarkably efficient. The global power grid already depends on it, with roughly 1/5 of all electricity generated by hydroelectric stations. The underlying source, the planet's water cycle, is self-sustaining. As long as the sun evaporates water and rain replenishes rivers, hydropower remains possible. It is, in effect, energy borrowed from the Earth's endless motion. Still, large dams come at a cost. Flooded valleys can destroy ecosystems and displace communities. Fish migration patterns can be disrupted, and changes in rainfall due to climate shifts can alter power availability. These are complex issues, yet engineers are exploring smaller scale and run-of-the-river hydro systems that minimize such impacts while preserving the benefits of clean, renewable electricity. Together, solar, wind, and hydro represent the vanguard of an energy revolution. They share a single defining trait: renewability. As long as the sun shines, the wind blows, and the water flows, these resources will remain available. They operate without consuming themselves, without poisoning their environment, without counting down toward exhaustion. Humanity stands at a threshold. The age of fossil fuels, once synonymous with progress, is giving way to something more enduring, a partnership with nature rather than a conquest of it. The question is no longer whether infinite energy sources can power the world, but whether we will choose to let them. Furthermore, infinite energy sources are far cleaner and more sustainable than any fossil fuel humanity has ever used. When we burn coal, oil, or natural gas, the air fills with carbon dioxide, sulfur compounds, and microscopic particles that harm both lungs and planet. These pollutants warm the earth, melt glaciers, and disrupt entire ecosystems. But the renewable forces of sunlight, wind, and water work differently. They generate power without releasing carbon emissions or choking cities in smoke. They run silently, leaving the air clear and the oceans calm. In this sense, they are not merely technologies. They are our chance to rewrite the story of civilization's energy. Solar, wind, and hydroelectric systems stand at the front lines of the global effort to halt climate change. When sunlight hits a solar cell, or when wind spins a turbine's blades, or when rivers surge through dams, electricity flows without fuel. These natural motions are endless, sustained by the planet's own rhythms. By using them, humanity can loosen its dependence on the fossil resources buried beneath the earth. Every megawatt generated by renewables means less coal dug from mountains, less oil drilled from fragile seabeds, and fewer gas flares lighting up desert skies. Reducing this extraction not only protects the environment, but also calms the geopolitical storms that swirl around oil-rich regions. Fewer nations would fight for control of finite reserves when the ultimate energy source shines above every roof and sweeps across every plain. Over time, infinite energy systems also prove less expensive. The cost of building solar farms, offshore wind platforms, or hydroelectric dams can seem daunting at first. Yet once installed, their operating costs drop sharply. A solar panel can hum quietly for decades, gathering sunlight and turning it into electricity without needing any refueling. A turbine can spin for years, powered only by the wind that never stops blowing. Unlike fossil fuels, there are no deliveries, no price spikes, no depletion. Infinite energy systems become cheaper the longer they run. At the frontier of these energy frontiers lies nuclear fusion, a phenomenon both ancient and new. Fusion is the extraordinary process by which two or more atomic nuclei, the dense cores of atoms, combine to form a single heavier nucleus. When this happens, a fraction of their original mass disappears, transformed into pure energy. This astonishing exchange is governed by Einstein's famous relationship between mass and energy. In stars, this reaction lights up the universe. Every sunrise is powered by fusion taking place inside the sun's blazing heart. Fusion, however, is not easy to achieve. It demands temperatures of millions of degrees, pressures so immense that atoms are forced to collide, and enough time for these collisions to occur before the plasma cools. Scientists summarize these requirements in a term called the triple product. Nature meets these conditions inside stars or in the brief fury of hydrogen bombs. Humans, however, must recreate them in laboratories and fusion reactors, machines designed to confine, heat, and sustain the plasma long enough for fusion to occur. The quest to do so has defined more than a century of physics. When fusion produces elements lighter than nickel-62, it releases energy rather than consuming it. Lighter atoms like hydrogen and helium are easier to fuse because their nuclei are loosely bound. The simplest fusion reactions involve isotopes of hydrogen, deuterium, which has 1 neutron, and tritium, which has 2. When deuterium and tritium unite, they form helium-4 and release a burst of energy in the form of a neutron moving at nearly 14 million electron volts. This reaction, if controlled, could power entire cities with no carbon, no smoke, and no long-lived radioactive waste. Fusion is distinct from fission, its nuclear counterpart. Fission splits heavy atoms like uranium or plutonium apart, releasing energy in the process. It powers current nuclear reactors but leaves behind radioactive waste that lasts for millennia. Fusion, by contrast, builds rather than breaks. It powers the stars, drives thermonuclear weapons, and serves as a key tool in laboratories that create super heavy elements. If tamed, it could supply Earth with an energy source nearly as boundless as the sun itself. The path to understanding fusion began more than a century ago. In 1915, American chemist William Draper Harkins first proposed that atomic fusion might release tremendous amounts of energy. 4 years later, Francis William Aston invented the mass spectrometer and discovered that 4 hydrogen atoms together weighed more than 1 helium atom. That tiny difference hinted at a hidden source of power. When hydrogen fuses into helium, the missing mass is converted into energy. In 1920, British astronomer Arthur Eddington took this insight further, predicting that fusion is the process that powers the stars. Around the same time, advances in quantum mechanics began to reveal how particles could overcome the repulsive forces that normally keep nuclei apart. German physicist Friedrich Hund described this phenomenon, and in 1928, Russian scientist George Gamow applied it to explain alpha decay and later nuclear fusion. His ideas inspired Robert Atkinson and Fritz Houtermans, who in 1929 calculated how often fusion reactions might occur inside stellar cores. By 1938, Hans Bethe and Charles Critchfield mapped out the proton-proton chain reaction, the main energy source of stars like the sun. Bethe also described another process, the CNO cycle, which dominates in larger, hotter stars. These discoveries connected the physics of atoms to the life cycle of the cosmos itself. Meanwhile, experiments on Earth began to turn theory into reality. In the 1920s, physicist Patrick Blackett carried out the first successful artificial nuclear reactions, transforming one element into another. In 1932, John Cockcroft and Ernest Walton, using equipment inspired by Gamow's ideas, achieved one of the first artificial fusion reactions by bombarding lithium with protons. Their experiment briefly created beryllium, existing for only a fraction of a second before decaying. At the University of California, early cyclotron experiments accidentally triggered deuterium fusion, though researchers did not yet recognize what had happened. In 1934, Australian physicist Mark Oliphant, working with Paul Hartek and Ernest Rutherford, deliberately fused deuterium atoms, producing both tritium and helium-3. This marked the first confirmed observation of nuclear fusion in a laboratory setting. 4 years later, in 1938, Arthur Ruark at the University of Michigan identified the deuterium-tritium fusion reaction, which emitted neutrons of astonishing energy, about 14 million electron volts. This became the foundational reaction for future fusion research and power generation. Since those pioneering years, scientists have pursued fusion through magnetic confinement devices like tokamaks and stellarators, as well as laser-driven inertial confinement systems. Each approach seeks to master the same challenge, containing a plasma so hot and dense that atomic nuclei overcome their natural repulsion and fuse. Every experiment, every spark brings humanity one step closer to replicating the power that lights the stars. If that day comes, when fusion burns steadily within reactors on Earth, the implications would be historic. Clean energy would no longer depend on weather, geography, or finite fuel. Nations could power industries, homes, and transport without carbon emissions or environmental destruction. Infinite energy would no longer be a dream of science fiction, but a foundation for civilization's next age of light. And during the early 1940s, fusion, the process that powers the stars, became not just a scientific curiosity, but a military priority. The world was at war, and the United States had launched the Manhattan Project, an unprecedented secret effort to build the first atomic weapons. In 1941, two of the most brilliant physicists of the era, Enrico Fermi and Edward Teller, met to discuss a radical idea, using the immense energy of a fission bomb to ignite fusion, the merging of atomic nuclei. Their conversation marked the beginning of humanity's attempt to recreate the power of the sun on Earth. By 1942, physicist Emil Konopinski had drawn attention to the earlier theoretical work of Arthur Ruark, bringing the possibility of fusion into the heart of the Manhattan Project. J. Robert Oppenheimer, the project's scientific director, discreetly assigned small teams to study whether fusion could occur under bomb-like conditions. From 1942 to 1946, they explored the physics in secret, trying to understand the thresholds of temperature and pressure needed to overcome the immense repulsive forces between atomic nuclei. At first, they assumed that deuterium-deuterium and deuterium-tritium reactions would behave much the same. But in 1946, a revelation came from physicist Egon Brecher, who discovered that the deuterium-tritium reaction was roughly 100 times more probable because of a resonance effect, an alignment of quantum states that made fusion far easier to achieve. This finding would become the foundation for all later thermonuclear weapon design. Meanwhile, at Los Alamos, scientists were beginning to use one of the earliest computers ever built, ENIAC. Starting in 1945, they used it to run mathematical simulations of fusion explosions, trying to model hydrogen bomb designs in digital form for the first time. The idea of harnessing fusion was no longer theoretical. It was being engineered. Then came the first experimental proof. In 1951, during the U.S. Greenhouse George test, researchers triggered a small-scale thermonuclear reaction using deuterium-tritium gas. The explosion released an energy equivalent to 225,000 tons of TNT, about 15 times the power of the bomb dropped on Hiroshima. Though it was only a glimpse of what was possible, it confirmed that fusion could indeed be achieved on Earth. The next year, in November 1952, the world witnessed the Ivy Mike experiment, the first true hydrogen bomb test. Using liquid deuterium as fuel, this two-stage device produced an astonishing explosion of over 10 million tons of TNT. The Teller-Ulam design, named after Edward Teller and mathematician Stanislaw Ulam, had succeeded. It used a primary fission bomb to create the conditions needed for fusion in a secondary stage, amplifying the energy release to unimaginable levels. The landscape of warfare and of human knowledge had changed forever. The Soviet Union was close behind. In 1953, it detonated the RDS-6, the first deliverable fusion bomb with a yield of about 400,000 tons. 2 years later came RDS-37, a true two-stage hydrogen bomb with a power output of 1.5 million tons of TNT. Their version of the Teller-Ulam idea was refined and deadly efficient. The arms race between superpowers had entered its most dangerous phase. Modern thermonuclear weapons now rely on solid lithium deuteride, enriched with lithium-6. During detonation, lithium-6 produces tritium, which then reacts with deuterium to unleash the powerful deuterium-tritium fusion reaction. The process also generates an intense burst of neutrons that sustain the chain reaction. It was an elegant but terrifying piece of physics, a weapon born from the same forces that light the cosmos. Yet even as militaries explored destruction, many scientists dreamed of the opposite, using fusion for peaceful power. Controlled fusion could, in theory, offer limitless clean energy. Efforts toward this goal began as early as the 1930s, but progress was slow. In 1958, at Los Alamos National Laboratory, a device known as SCILA, the FR machine, achieved the first fusion reactions in a controlled laboratory setting. It was a small spark of hope in the shadow of the hydrogen bomb. From that point onward, the challenge was clear: how to contain and sustain fusion safely without an explosion. Decades of research followed. In the United States, the National Ignition Facility, or IF, was built to pursue a method called inertial confinement fusion. In this approach, ultra-powerful lasers compress and heat a small fuel pellet until its nuclei fuse. The dream was to reach ignition, the moment when the reaction produces more energy than it consumes. Scientists called this point break-even, when the energy gain factor rises above 1. Construction of NIF began in the early 2000s, and the first major experiments took place in 2009. More serious ignition trials started in 2011. Then, on December 5, 2022, history was made. The NF team focused lasers delivering 2.05 megajoules of energy onto a fusion target. The result? A release of 3.15 megajoules, more energy out than in. For the first time ever, a controlled fusion reaction had achieved net gain. On December 13th, the U.S. Department of Energy announced this to the world. It was a turning point, proof that the fusion dream was no longer just theory. There are two main routes to achieving fusion power: The first is magnetic confinement, which uses strong magnetic fields to trap superheated plasma inside donut-shaped reactors known as tokamaks. The second is inertial confinement, the laser-driven technique used at NIF, a massive international project called ITER, the International Thermonuclear Experimental Reactor, is now under construction in southern France. Its goal, to produce 10 times more fusion energy than it consumes. ITER is expected to complete its main structure by 2025, begin testing soon after, and attempt full deuterium-tritium fusion reactions by 2035. Fusion energy has also moved beyond governments. In 2021, private companies attracted about $6 billion in investment. However, there's also another powerful player in the subatomic world, the nuclear force. It's a strong but extremely short-range force that binds protons and neutrons together within the nucleus. Without it, no atom larger than hydrogen could exist. For the smallest, lightest elements, like hydrogen and helium, the nuclear force can overcome the electric repulsion between positively charged protons. When this happens, the atomic nuclei merge. This merging, called nuclear fusion, creates a new nucleus that weighs slightly less than the sum of its parts. That missing mass doesn't vanish, it transforms into pure energy. This is not just a laboratory concept. Fusion is the engine of the universe. It's what makes the stars shine, including our own sun. Every second, the sun fuses about 620 million metric tons of hydrogen into about 616 million metric tons of helium. The tiny 4 million ton difference becomes radiant energy that streams across space, reaching Earth as sunlight and warmth. Even though the mass difference is only about 0.645%, the amount of energy produced is staggering. That small conversion is enough to keep the sun shining with the brightness of nearly 400 trillion 60-watt light bulbs. But there's a limit. Fusion works only for lighter elements. In heavier elements, the balance between the nuclear attraction and electric repulsion changes. The nuclear force, powerful as it is, cannot pull large nuclei close enough to fuse efficiently. As a result, trying to fuse heavier elements consumes more energy than it releases. In the simplest case, 2 hydrogen nuclei fuse to form helium. In the process, a tiny fraction of their mass becomes energy. Some of that energy appears as light, some as fast-moving particles, kinetic energy. But forcing 2 positively charged nuclei close enough to touch requires enormous pressure and temperature. Once they're close enough, though, the nuclear force takes over, draws them together, and releases a burst of energy. These reactions are called exothermic. They give off energy. Fusion reactions are far more powerful than chemical reactions. For instance, when a hydrogen atom captures an electron, it releases about 13.6 electron volts of energy. In contrast, when a deuterium nucleus fuses with a tritium nucleus, the reaction releases about 17.6 million electron volts. That's more than 1 million times greater energy from a single atomic interaction. Fusion also surpasses nuclear fission, the process used in today's nuclear power plants. Fission splits heavy atoms like uranium, converting about 0.7% of their mass into energy. Fusion does roughly the same, but with lighter elements and with cleaner byproducts. Even so, both processes are dwarfed by the theoretical limits set by the universe's most extreme phenomena. Black holes can convert up to 40% of mass into energy. Antimatter annihilation can reach 100%. To imagine the scale, if just 1 gram of ordinary matter could be fully converted into energy, it would release about 90 trillion joules, enough to power an entire city for a day. Yet fusion is more than a source of energy. It is also the cosmic forge that built most of the elements around us. During the Big Bang, the first nuclei, hydrogen, helium, and traces of lithium were created. Later, inside stars, fusion built all the elements up to iron. Heavier elements, such as gold and uranium, formed through even more dramatic events, supernova explosions and collisions of neutron stars. These violent moments triggered the so-called slow and rapid neutron capture processes, known as the S process and R process. Together, they filled the universe with the elements that make up planets, oceans, and life itself. As stars grow old, their internal fusion changes. They burn through hydrogen, then begin fusing helium, carbon, oxygen, and other heavier elements, each stage shorter than the last. Eventually, fusion stops when the core is filled with iron. At that point, no further fusion can produce energy. The star collapses or explodes, scattering its enriched material across the galaxy. That stardust later becomes part of new stars, planets, and living organisms. Every atom of carbon in your body, every bit of oxygen you breathe, and every calcium atom in your bones was once created by a star's fusion furnace. Back in the early 20th century, the true nature of this process was still a mystery. In 1920, British astrophysicist Arthur Eddington proposed a bold idea. He suggested that stars derive their energy by turning hydrogen into helium, releasing immense amounts of energy in the process. It was a visionary leap. At that time, scientists weren't even sure that stars were mostly made of hydrogen. Eddington's insight, described in his paper, The Internal Constitution of the Stars, was based on Einstein's new equation, E equals mc squared, which showed that mass and energy are interchangeable. Eddington didn't know the precise mechanism, but he correctly identified fusion as the ultimate source of stellar power, decades before it was proven. Before Eddington's hypothesis, scientists believed in the contraction theory. According to this idea, stars shone because they were slowly shrinking, converting gravitational energy into heat. The logic came from observing spinning skaters. As they pull in their arms, they spin faster, conserving angular momentum. But when astronomers studied Cepheid variable stars, stars that pulse rhythmically in brightness, they noticed they were not spinning faster at all. The contraction theory could not account for the energy output of stars that remained stable for billions of years. The missing explanation came from a series of breakthroughs. Albert Einstein had shown that even a small amount of matter could be converted into enormous energy. Then, in the 1920s, British scientist Francis Aston made a crucial measurement. He discovered that 4 hydrogen atoms combined into 1 helium atom weigh slightly less, about 0.8% less to be exact. This discrepancy was the key. That missing mass, when multiplied by the speed of light squared, equals the energy radiated by stars. At the time, scientists thought atomic weight determined an element's identity. But research by Henry Moseley and Antonius van den Broek revealed that the true defining property of an element is its atomic number, the number of protons in the nucleus. Helium has 2 protons, hydrogen has 1. When 4 hydrogen nuclei fuse into 1 helium nucleus, that transformation releases energy according to Einstein's formula. Aston's measurement, combined with Einstein's insight, gave scientists the first quantitative proof that fusion could power the stars, and the numbers added up perfectly. If just 5% of a star's mass were hydrogen capable of fusing, that alone could sustain the star's brightness for billions of years. Today, fusion research on Earth tries to replicate what stars do naturally. Inside the Sun, gravitational pressure and temperatures of 15 million degrees force hydrogen nuclei close enough to fuse. On Earth, we try to achieve the same with powerful magnetic fields or lasers, heating hydrogen isotopes to more than 100 million degrees. Each experiment is a step toward harnessing the same process that lights up the cosmos. Fusion is the story of creation itself. From the first moments after the Big Bang to the shining of distant galaxies, it's the thread that connects matter, energy, and life. The universe, in its simplest terms, runs on fusion, and so do we, made from the ashes of stars that burned long ago. And today, we understand with extraordinary precision that almost every ordinary star is composed primarily of hydrogen, about 70 to 75% of its mass. It is the simplest and most abundant element in the universe, and it fuels the light that fills our skies. In the early 20th century, long before the atomic age began, scientists suspected that these luminous spheres might be more than just burning gas. They proposed that inside their immense interiors, hydrogen and helium might fuse together under unimaginable pressure, forming heavier elements and releasing vast quantities of energy. But at the time, the technology to measure atomic masses or detect nuclear reactions did not yet exist. The idea remained speculation, brilliant but unproven. Over the following decades, that speculation solidified into one of the great triumphs of modern science. With better telescopes, particle detectors, and the rise of nuclear physics, humanity uncovered the truth. Stars are natural fusion reactors. Our own sun, for instance, draws its power from a process known as nuclear fusion. Deep in its core, where the temperature reaches about 14 million Kelvin and the density is greater than 10 times that of solid lead, hydrogen atoms are compressed so tightly that they merge into helium. This particular reaction, called the proton-proton chain, converts 4 individual hydrogen nuclei into one helium nucleus, known as an alpha particle. In that transformation, 2 positrons, the antimatter counterparts of electrons, and 2 nearly massless neutrinos are emitted. They help convert 2 of the protons into neutrons, stabilizing the new helium nucleus. The energy released is enormous, spreading first through radiation and convection inside the sun before it escapes into space as sunlight. Every ray that reaches Earth is a whisper of that ancient fusion process, continuing uninterrupted for more than 4 billion years. But not all stars follow exactly the same recipe. In larger and hotter stars, another mechanism called the CNO cycle dominates. It uses carbon, nitrogen, and oxygen as catalysts to fuse hydrogen more rapidly. As these massive stars evolve, their internal furnaces shift to heavier fuels. First helium, then carbon, neon, oxygen, and silicon. Eventually, the chain of fusion ends at iron and nickel, where the physics itself sets an unbreakable boundary. Fusing nuclei heavier than nickel requires more energy than it produces. At that stage, the core of the star can no longer support its own weight, and collapse becomes inevitable. The death of such a massive star gives rise to some of the most spectacular events in the cosmos, supernova explosions. During these brief, violent moments, conditions become extreme enough to forge elements heavier than iron, gold, uranium, lead, through processes called the S process and the R process, slow and rapid neutron captures that build up the periodic table one particle at a time. The debris from these explosions scatters across galaxies, seeding future stars, planets, and even life itself. Not every object in the stellar family achieves such grandeur. Some, like brown dwarfs, never ignite true hydrogen fusion. They occupy a strange middle ground between giant planets and small stars. The largest of them can briefly fuse deuterium, a heavier form of hydrogen, and even traces of lithium, before fading into dim, reddish obscurity. White dwarfs, on the other hand, are the dense, glowing remnants of medium-sized stars like our Sun. Composed mostly of carbon and oxygen, a white dwarf can be no larger than Earth, but may weigh as much as the Sun. If it draws in too much material from a companion star and approaches what physicists call the Chandrasekhar limit, about 1.4 times the Sun's mass, a runaway fusion reaction can erupt, obliterating the star in a thermonuclear explosion known as a Type 1a supernova. Some remnants go further still. When a massive star collapses, its protons and electrons are crushed together to form neutrons, creating a neutron star, an object so dense that a teaspoon of its matter would weigh billions of tons. These stars can steal gas from nearby companions, triggering violent bursts of fusion across their surfaces. Within a single second, they can unleash more energy than the Sun emits in a week. In even more extreme environments, near black holes, fusion can occur in the superheated disks of gas that spiral inward. The gravitational energy there is converted into heat, driving nuclear reactions that vary depending on distance from the event horizon. At a few Schwarzschild radii, helium and carbon may fuse. Closer still, more exotic reactions, like those involving oxygen, neon, and even silicon, can occur in flashes of unimaginable intensity. Rewind the cosmic clock even further to just 10 seconds after the Big Bang. The young universe was a sea of pure energy and subatomic particles. As it expanded, it cooled from hundreds of thousands of kiloelectron volts down to about 1 kiloelectron volt in only 20 minutes. During this brief window, protons and neutrons combined to form the first atomic nuclei: deuterium, tritium, helium-3, and especially helium-4, with faint traces of lithium, beryllium, and boron. This was the era of primordial nucleosynthesis, when matter as we know it first took shape. Fusion, however, is not an easy process. Because atomic nuclei carry positive charges, they repel each other through the electrostatic, or Coulomb force. Overcoming this repulsion requires tremendous heat and pressure, conditions that exist only in the hearts of stars or in man-made reactors. Quantum mechanics provides a subtle advantage. Through a phenomenon called quantum tunneling, particles can sometimes leak through the energy barrier even when they lack the energy to climb over it. Without this effect, fusion in the Sun would be impossible. Inside each nucleus, protons and neutrons, collectively known as nucleons, are held together by the strong nuclear force, a powerful but short-range attraction. A nucleon feels this force only from its immediate neighbors, so those in the center of a nucleus are bound more tightly than those near the surface. Small nuclei having a larger surface area relative to their volume possess less binding energy per particle. As nuclei grow larger, their binding energy increases but eventually plateaus at around the size of iron and nickel. Beyond that point, additional protons only increase repulsion, making the nucleus less stable. The tug of war between the strong nuclear force and electrostatic repulsion defines the architecture of matter itself. The electrostatic force follows the inverse square law. Double the distance between two charged particles, and the attraction or repulsion becomes 4 times weaker. In heavy nuclei with many protons packed close together, this repulsive energy grows faster than the binding energy from the strong force. That is why superheavy elements decay quickly. They simply cannot hold themselves together. Among all known isotopes, the most tightly bound are nickel-62, iron-58, iron-56, and nickel-60. Of these, nickel-62 has the highest binding energy per nucleon, yet iron-56 dominates in abundance because stellar fusion naturally produces it more efficiently through the alpha process. Helium-4 stands as a special case. Its nucleus, 2 protons and 2 neutrons, is extraordinarily stable, more so than lithium or beryllium. The reason lies in quantum mechanics. Protons and neutrons are fermions, and the Pauli exclusion principle states that no 2 identical fermions can occupy the same quantum state simultaneously. In helium-4, the particles pair up in a perfectly balanced configuration, minimizing energy and maximizing stability. From the first few minutes after the Big Bang to the glowing cores of stars today, fusion has been the universe's great engine of creation. Every element heavier than hydrogen owes its existence to these thermonuclear furnaces, each acting as a forge in an ongoing cosmic narrative that spans billions of years. Every atom in our bodies, carbon in our cells, calcium in our bones, iron in our blood, was once part of that story, born from the heart of a star and carried across space by the grand chemistry of the cosmos. However, each energy level within an atomic nucleus can accommodate only 2 particles, one spinning upward, the other spinning downward. This fundamental rule of quantum mechanics gives the helium-4 nucleus its remarkable stability. It contains exactly 2 protons and 2 neutrons, and those 4 particles fill the lowest possible energy state with perfect symmetry. The result is a nucleus so tightly bound that scientists often treat it not as a cluster of particles, but as a single, unified entity, a particle in its own right. In nuclear physics, it is known by a different name, the alpha particle. Now imagine trying to force 2 nuclei to meet. As they approach each other, an invisible yet powerful battle begins. Every proton in one nucleus repels every proton in the other through the electrostatic or Coulomb force, the same force that causes 2 positively charged magnets to push apart. This repulsion creates what physicists call the Coulomb barrier, a wall of electrical resistance that must somehow be overcome for fusion to occur. Yet nature provides a loophole. If the nuclei come close enough, even for a fleeting instant, the strong nuclear force, the fundamental interaction that binds protons and neutrons together, can suddenly overpower the repulsion and pull the 2 nuclei into a single larger one. But how do they ever get that close? Here, quantum mechanics provides an astonishing twist. Particles are not tiny billiard balls. They also behave like waves. This means there is always a small chance that they can tunnel through an energy barrier instead of climbing over it. This process, known as quantum tunneling, allows fusion to happen even when the nuclei don't seem to have enough energy to overcome the Coulomb barrier directly. The barrier is smallest for hydrogen, the simplest element of all, made from a single proton. A nucleus composed only of 2 protons, known as a diproton, is unstable. It breaks apart almost instantly. To achieve fusion, neutrons must be involved. The goal is usually to form helium because helium's nucleus is one of the most tightly bound configurations in nature. That tight binding releases enormous energy when it forms. Scientists often use a mixture of 2 heavier types of hydrogen, deuterium, which contains 1 proton and 1 neutron, and tritium, which has 1 proton and 2 neutrons. This deuterium-tritium combination is the most efficient fusion fuel known. It requires an energy input of about 1/10 of 1 million electron volts, or 0.1 MeVs, to initiate the reaction. For comparison, it takes only 13.6 electron volts to strip a single electron from a hydrogen atom. In other words, fusion demands energies roughly 10 million times greater than the process of ionizing hydrogen. When deuterium and tritium finally fuse, they briefly create an unstable nucleus of helium containing 5 particles. Almost instantly, this new nucleus ejects a neutron carrying around 14.1 MeV of energy, while the remaining helium-4 nucleus recoils with about 3.5 MeV. Together, they release 17.6 MeV of energy, far more than what was required to start the reaction. This tremendous energy yield is what makes fusion so promising as a potential power source. To measure how likely fusion is to occur, physicists use a quantity called the reaction cross-section, symbolized by the Greek letter sigma. It represents the probability that 2 nuclei will fuse when they collide. The faster the nuclei move toward each other, the higher the likelihood of fusion. In the superheated environment of a plasma, a gas so hot that electrons are stripped from their atoms, nuclei move at a wide range of speeds. Scientists average the product of sigma and velocity across all these speeds and call this average reactivity. The total rate of fusion in a given region depends on both this reactivity and the number of nuclei present. For identical nuclei, such as 2 deuterium atoms fusing, reactivity is essentially 0 at room temperature. But as temperatures rise into the range of 10,000 to 100,000 electron volts, the probability of fusion increases dramatically. At these extraordinary temperatures, far beyond what binds atoms together, matter exists only as plasma, a seething ocean of charged particles. The interplay between temperature, reactivity, and how long the plasma can hold its energy leads to what scientists call the Lawson criterion. This condition determines whether a fusion reaction can produce more energy than it consumes. Meeting the Lawson criterion on Earth is one of the greatest scientific challenges ever undertaken, and it explains why fusion power remains a goal pursued for decades rather than an achievement already realized. Thermonuclear fusion, the process of forcing atomic nuclei to combine, lies at the heart of both the stars and our technological dreams. In the cores of stars like the Sun, fusion occurs naturally, providing the light and warmth that sustain life on Earth. The same process, unleashed all at once, powers hydrogen bombs. The challenge is to control it, to reproduce the Sun's energy, but in a stable and continuous way. Temperature measures how fast and energetic particles are moving. In fusion, the temperature must be so high that the nuclei collide with enough force to overcome their mutual repulsion. The exact temperature required depends on the Lawson criterion and on the type of fuel used. For deuterium and tritium, the necessary particle energy is about 0.1 million electron volts, corresponding to a temperature of roughly 1,200,000,000 Kelvin, hotter than the center of the Sun itself. Yet fusion can occur even below that threshold. There are 2 reasons. First, not every particle in a plasma has the same energy. Some occupy what physicists call the high-energy tail of the distribution, giving them a better chance to fuse. Second, quantum tunneling once again offers a way through the barrier, allowing fusion to occur even when the classical energy requirements are not met. If scientists can master this process, thermonuclear fusion could become one of the cleanest and most sustainable energy sources on Earth. It produces no greenhouse gases and no long-lived radioactive waste. The fuel, hydrogen, is abundant in seawater. It could power civilization for millions of years without harming the planet. Among the many paths toward achieving controlled fusion, one of the simplest conceptually is called accelerator-based light-ion fusion. In this method, particle accelerators speed up light ions, such as protons or deuterons, and slam them into one another at immense velocities. The setup is surprisingly minimal: a vacuum chamber, 2 electrodes, and a high-voltage power source. Fusion reactions can begin with voltages as low as 10,000 volts between the electrodes. There are 2 principal configurations. In beam-target fusion, a beam of accelerated ions strikes a stationary target containing fusion fuel. In beam-beam fusion, 2 opposing streams of ions collide in midair, increasing the chances of interaction. Both methods demonstrate the same fundamental truth. When the conditions are right, even the tiniest building blocks of matter can overcome their mutual repulsion and merge into something new, releasing a burst of energy that once powered the stars and may someday power our world. However, this method faces a significant obstacle. Most of the ions that are meant to fuse never actually do. Instead, they lose their energy in less useful ways, by emitting X-rays known as Bremsstrahlung radiation, or by colliding with atoms in the target and knocking their electrons loose. In the controlled chaos of a fusion chamber, every ion carries the potential to release enormous power, yet most of that potential is lost before it can unite with another nucleus. To harness even a fraction of this process, engineers developed a compact and efficient device called a sealed tube neutron generator. This instrument is a miniature particle accelerator filled with deuterium and tritium gases. Inside its metal casing, charged particles are accelerated toward a target that also contains fusion fuel. When the ions strike the target, tiny bursts of nuclear fusion occur, releasing a flash of neutrons. Though each burst is small, the device is reliable and repeatable. Hundreds of these generators are built every year, primarily for the oil and gas industry. When lowered deep into boreholes, the neutrons they emit interact with surrounding rock, helping geologists map underground oil and water reservoirs. Over the years, scientists have tried to make the process more efficient by reusing the ions that miss their mark. In the 1970s, a concept known as MIGMA attempted to trap these energetic particles in circular magnetic orbits. The idea was that, instead of being wasted, the ions would keep circling until they eventually collided and fused. The principle was elegant, but the physics proved unforgiving. Experiments showed that at the scale required for power generation, the ions would still lose too much energy to radiation and scattering. The dream of self-sustaining magnetic recirculation faded, yet innovation did not stop. In the 1990s, physicist Norman Rostoker proposed a new approach called the field-reversed configuration, or FRC. This system aimed to confine plasma in a self-stabilizing magnetic field shaped like a smoke ring. Decades later, Rostoker's ideas inspired TAE Technologies, a California-based company still working to make FRC fusion practical. A related concept involves colliding two spinning FRCs at high speed. Another company, Helion Energy, is developing this method, hoping that the intense collision of the plasma rings will yield more energy than is consumed. Such techniques push ions to far higher energies than in traditional fusion systems, opening the door to fuels that are usually too difficult to use, like proton-boron 11. If successful, these fuels could produce vast energy with almost no radioactive waste, a potential revolution for clean power. Fusion, however, is not limited to energy production. It has also been the key to creating new elements. In the early 1930s, scientists bombarded materials with deuteron beams, leading to the discovery of synthetic elements such as technetium, neptunium, and plutonium. Today, laboratories use heavy ion accelerators to forge super-heavy elements, atomic giants that exist for only fractions of a second before decaying. Each discovery expands our understanding of the forces that hold matter together. There is even a form of fusion that happens at room temperature. It is called muon-catalyzed fusion, first studied seriously in the early 1980s by physicist Stephen Jones. This process relies on particles known as muons, which can replace electrons and bring atomic nuclei extremely close together, close enough for fusion to occur without immense heat. But there is a serious limitation. Producing muons consumes far more energy than the fusion releases, and muons themselves are short-lived, surviving only about 2.2 millionths of a second. Many also become stuck to fusion products and can no longer catalyze new reactions. As a result, the process remains a scientific curiosity rather than a viable energy source. Other unconventional ideas have surfaced as well. Antimatter-initiated fusion proposes using minuscule quantities of antimatter to trigger compact fusion explosions. The concept has been investigated mainly for spacecraft propulsion or advanced weaponry, but the cost of producing antimatter makes it impractical for civilian energy use. Another experimental technique, pyroelectric fusion, appeared in 2005 when researchers at UCLA demonstrated that certain crystals can generate powerful electric fields as they are heated or cooled. By warming a crystal from -34 degrees Celsius to 7 degrees, They created a voltage strong enough to accelerate deuterium ions into a metal target, producing measurable helium and neutrons. The energy output, however, was still smaller than the energy required to drive the process, limiting the device to scientific and industrial neutron generation. The search for hybrid systems where fusion and fission work together has persisted for decades. The idea first surfaced in the 1950s and gained some attention in the 1970s when physicist Hans Bethe explored whether such a system could use fusion neutrons to sustain fission reactions. Interest faded for a time, but returned in 2009 as researchers sought practical bridges between existing nuclear technology and future fusion systems. One of the most audacious efforts came from Project PACER at Los Alamos National Laboratory during the mid-1970s. Its engineers proposed detonating small hydrogen bombs inside underground cavities to produce power. Unlike other fusion concepts, this one was technically feasible with existing knowledge. The challenge, however, was political and economic. A reactor that depended on a continuous supply of nuclear explosives was not a sustainable or safe energy source. In the early 2000s, another controversial concept emerged, bubble fusion or sonofusion. The idea suggested that high-intensity sound waves could create microscopic bubbles in a liquid that collapse with such force they briefly reach fusion temperatures. The claim attracted attention but could not withstand scrutiny. Repeated attempts to replicate the results failed, and the lead researcher, Rusi Taliarkhan, was later found guilty of research misconduct in 2008. Whether magnetic, inertial, or acoustic, all fusion systems share the same goal: to confine plasma long enough for atomic nuclei to merge. In stars, gravity provides that confinement naturally, pressing matter together under colossal pressure. On Earth, scientists must rely on magnetic fields, as in tokamaks and stellarators, or on the inertia of rapidly imploding fuel pellets, as in laser-driven experiments. In both cases, success depends on meeting the Lawson criterion, the balance between temperature, density, and confinement time required for fusion to sustain itself. Fusion remains one of humanity's grandest scientific challenges. Each experiment, whether it succeeds or fails, brings us a step closer to mastering the process that powers the stars. However, the amount of mass required for gravitational confinement is almost beyond imagination. Only in the cores of stars does nature find enough matter to hold fusion reactions steady. In these cosmic furnaces, gravity acts as both cage and catalyst, crushing hydrogen atoms together until they merge and release light. The smallest of these stars, the red dwarfs, burn dimly but for extraordinary spans of time, trillions of years, fusing hydrogen into helium at a slow, steady pace. Larger than red dwarfs, but smaller than full-fledged stars, are brown dwarfs, often described as failed stars. They lack the mass to sustain long-term hydrogen fusion, but can briefly ignite reactions involving deuterium and lithium if their mass is sufficient. As stars grow in size and evolve, their internal pressures and temperatures climb. When their hydrogen fuel is exhausted, fusion does not stop, it transforms. Helium nuclei begin to fuse into carbon, and in more massive stars, this chain of reactions continues up the periodic table. Oxygen, neon, silicon all appear as the stellar furnace rearranges atomic building blocks into heavier forms. Yet there is a natural limit to this cosmic alchemy. Once a star begins to form iron in its core, the game changes. The fusion of iron no longer yields energy, it consumes it. Iron marks the boundary where stellar fusion can no longer pay its energetic debt. When that limit is reached, the most massive stars die spectacularly. Their cores collapse, gravity overwhelms matter, and the outer layers rebound outward in a blinding explosion, a supernova. In that brief, violent instant, temperatures rise to levels where even heavier elements are forged. Gold, uranium, and other dense materials are created not by quiet fusion, but by chaos and collapse. These newly minted atoms scatter across space, later to form planets, oceans, and eventually the chemistry of life itself. Some smaller stars also play a part. Through neutron capture and energy absorption, they build heavier elements in their outer layers, adding subtle contributions to the cosmic inventory. Every atom heavier than iron carries within it the memory of violence, the stored energy from stellar nucleosynthesis that occurred billions of years ago. To confine fusion artificially on Earth, Scientists must find substitutes for the gravitational pressure that stars naturally possess. One method uses magnetism. Charged particles, such as fusion fuel ions, spiral along magnetic field lines, allowing strong magnetic fields to trap the plasma and prevent it from touching reactor walls. Devices like tokamaks and stellarators use toroidal or donut-shaped fields to achieve this. Another magnetic concept, mirror confinement, employs magnetic bottles that reflect particles back and forth between field lines. Beyond magnetism lies a more explosive idea, inertial confinement. Instead of steady containment, it relies on speed and compression. A small pellet of fusion fuel, often a frozen mixture of deuterium and tritium, is struck with immense energy, usually from lasers or ion beams. The outer layer vaporizes, driving the inner material inward in an implosion so rapid that the core's pressure and temperature soar to fusion conditions. The same physical principle underlies the hydrogen bomb, where X-rays from a fission explosion compress the fusion core. Researchers now attempt to control this process precisely without the destructive force of a bomb, using advanced laser systems, electron beams, or Z-pinch devices that squeeze plasma with electric currents. Even conventional explosives have been tested for controlled implosion, such as in the UTAS explosive-driven facility, which generated focused hemispherical implosions that briefly produced deuterium-deuterium fusion neutrons. There is also electrostatic confinement, where ions are held not by magnetism or inertia, but by electric fields. The Farnsworth-Hirsch fusor is the best-known example. Inside it, a grid with a negative charge attracts positively charged deuterium ions toward the center, where they collide and sometimes fuse. The device is simple enough that skilled enthusiasts have built working versions at home, successfully creating minute amounts of fusion since 1999. However, efficiency remains extremely low due to ion collisions and energy losses. To overcome these limits, scientists experiment with variants such as polywells, penning traps, and oscillating plasma devices. Each seeks a balance between confinement, energy input, and particle behavior, but all remain experimental. Inside stars, by contrast, fusion occurs with deceptive slowness. In the core of our Sun, at roughly 15 million Kelvin and a density of about 160 grams per cubic centimeter, the rate of fusion produces only about 276 microwatts of energy per cubic centimeter. This is less than the heat generated by a resting human body. The sun shines not because fusion there is fast, but because it happens on an unimaginable scale, across a sphere more than 1 million kilometers wide. Trying to recreate such conditions in a laboratory introduces extreme challenges. Since we cannot match the density of stellar matter, we compensate with higher temperatures, between 10 and 100 times greater than the sun's core. That means reaching around 100 million to 1 billion Kelvin. Under these conditions, different fuels can be used, not limited to simple protons. Deuterium and tritium are the most common choices because they fuse more readily at lower energies, producing helium and a fast neutron. Neutrons, while useful for carrying away fusion energy, also pose a problem. They can make the reactor's structure radioactive over time, yet their presence allows energy extraction and enables breeding of tritium, an isotope of hydrogen needed for continued operation. Reactions that avoid neutron production altogether are called aneutronic reactions. These are cleaner but much harder to achieve due to higher temperature requirements. For any fusion process to serve as a practical energy source, it must meet strict criteria. It must be exothermic, releasing more energy than it consumes. The nuclei must be light, low on the periodic table, so that the repulsive electric forces between them are small enough to overcome. 2 reactants are preferred. Collisions involving 3 nuclei are almost impossible except at stellar densities. Most reactions also produce 2 or more products, ensuring conservation of both energy and momentum without invoking complex electromagnetic corrections. The weak nuclear force rarely plays a role in fusion, so proton and neutron numbers remain stable during most reactions. When 2 products emerge from a fusion event, their energy divides inversely with their masses. The lighter particle carries the greater share. In reactions producing 3 products, energy spreads more variably. Some fusion reactions can lead to multiple outcomes, and scientists describe their relative probabilities using branching ratios. Certain candidate reactions can be ruled out quickly. For instance, Deuterium-lithium-6 fusion produces as many neutrons as the proton-boron-11 reaction, but is harder to ignite. The proton-lithium-7 pathway also looks promising but requires temperatures exceeding 1 million electron volts, far higher than most reactors can withstand. At those extremes, even endothermic reactions that absorb energy begin to occur, complicating efforts to harvest useful power. In the search for controlled fusion, humanity stands between the patience of stars and the precision of machines. The forces that light the cosmos can, in principle, illuminate our cities. But taming a star inside a magnetic field or a glass sphere remains one of the most ambitious challenges in science, a pursuit not only of energy, but of understanding how the universe itself forges its light. And finally, we arrive at one of the most intricate and fascinating nuclear processes, the proton-beryllium-9 reaction. It is a reaction that refuses to cooperate easily. Not only is it difficult to ignite, but it also produces beryllium-9, an isotope that is unstable and prone to splitting into two alpha particles and a neutron. This chain of events illustrates both the promise and peril of fusion science. Reactions that hold immense potential for power, but are governed by forces that resist control. Beyond fusion itself, neutron-based reactions play a crucial supporting role. They are particularly important in the creation of tritium, an isotope of hydrogen essential for both dry fusion bombs and for future fusion reactors. One historical moment that revealed the complexity of these reactions came during the United States Castle Bravo test in 1954. It was only the second fusion bomb ever detonated, and the first to incorporate lithium. The scientists at the time understood how lithium-6 could generate tritium when bombarded with neutrons. What they underestimated was the contribution of lithium-7. Though lithium-7 interacts only weakly with low-energy neutrons, its cross-section, the likelihood of interacting, rises dramatically when the neutron energy exceeds 5 million electron volts. This oversight had explosive consequences. The bomb yielded 15 megatons, more than double the expected 6, releasing catastrophic levels of fallout and exposing nearby observers and island populations to severe radiation. To measure and predict the effectiveness of any nuclear fusion process, scientists must weigh several interlocking variables: the types of reactants involved, the products they form, the total energy released, and the nuclear cross-section that quantifies how easily nuclei collide and merge. Every fusion device has an upper limit on the plasma pressure it can safely sustain. The most efficient designs push right to this threshold, balancing on the knife edge between containment and collapse. At that point, the fusion output peaks when the temperature is tuned so that the ratio of the product of the fusion cross-section and particle velocity divided by the square of the temperature is maximized. The temperature that satisfies this condition also minimizes the so-called triple product, the key requirement for ignition, since it is inversely proportional to that same ratio. A plasma is said to be ignited when its own fusion reactions release enough energy to maintain the required temperature without external heating. Any of the reactions we've discussed could, in principle, serve as a foundation for power generation, but each brings its own engineering and physical challenges. In addition to temperature and cross-section, we must also evaluate how the energy divides between charged and uncharged particles, and how the atomic structure of the heavier non-hydrogenic elements affects reaction dynamics. The deuterium-deuterium reaction, often written as DD, offers a useful example. It presents two major complications. First, it proceeds through two different branches that must be averaged to calculate an overall reaction rate. Second, it generates tritium and helium-3, both of which behave in tricky ways inside a plasma. Tritium, once formed, fuses so quickly with deuterium that extracting it from the plasma is nearly impossible. Meanwhile, helium-3 burns at much higher temperatures, meaning that at the optimal DD temperature, its reaction rate remains low. The net effect is that tritium becomes a transient participant, feeding back into the system and adding to the total energy produced. Because DD fusion involves only one type of reactant, the rate equations must account for that fact. Each nucleus can collide with any other of its kind, making the reaction inherently faster per particle than mixed fuel systems. Four of the most important fusion reactions can be summarized by their neutronicity. The fraction of total energy released as neutrons, rather than charged particles. Neutronicity is not just a number, it defines the practical difficulty of building a reactor. High neutron fluxes cause radiation damage, demand heavy shielding, complicate remote handling, and introduce safety hazards. For reactions like deuterium, tritium, and deuterium helium-3, scientists calculate neutronicity as the ratio of the energy carried away by neutrons to the total fusion energy. For more advanced reactions with negligible neutron output, the value is estimated based on side processes that occur in a thermal plasma. Achieving optimal fusion conditions requires precise balance between reactants. The ideal mixture occurs when each ion species, along with its accompanying electrons, contributes equally to the total pressure. If we hold pressure constant, the number density of non-hydrogenic ions such as helium, boron, or lithium must be half that of hydrogenic ions. Mathematically, this relationship is described by a factor of 2 divided by the atomic number plus 1. Because of this ratio, reactions involving heavier nuclei proceed more slowly, partly because extra electrons add to pressure without contributing to fusion itself. This introduces a penalty factor that makes non-hydrogenic fuels less efficient. Yet, the situation is not entirely disadvantageous. Single-species reactions, like DD, gain an intrinsic bonus. Each ion can react with every other ion, effectively doubling the number of possible interactions. In contrast, mixed fuel systems split their reactants between two species, cutting potential collisions in half. Thus, in practice, the DD reaction benefits from a statistical advantage, even though it operates at higher temperatures and produces lower energy per fusion event. When scientists compare alternative fuels, they calculate a penalty bonus factor that expresses how much slower or faster one reaction proceeds relative to the benchmark deuterium-tritium DT reaction. Additional columns of comparison tables include the Lawson criterion, a measure of how much harder it is to achieve ignition compared to DT, and power density, which quantifies how much energy can be extracted per unit volume of plasma. These values reveal the economic and technical trade-offs of different fusion pathways. In real-world reactors, plasma consists not only of ions, but also of a swarm of electrons that maintain electrical neutrality. These electrons, often at similar or even higher temperatures than the ions, collide frequently, emitting X-rays in a process called Bremsstrahlung radiation. In stars such as the Sun, the immense scale prevents these X-rays from escaping. Instead, they are reabsorbed, recycling their energy and keeping the stellar plasma luminous and stable. On Earth, however, reactors are far too small to trap these photons. The X-rays escape, striking the reactor walls, often made of stainless steel, and depositing their energy there. The result is cooling of the plasma and heating of the structure, a constant battle between containment and loss. Therefore, when engineers design a fusion reactor, one of the most critical performance ratios is that between fusion power generated and X-ray power lost. This ratio determines the efficiency of confinement and the viability of sustained operation. Interestingly, the temperature that optimizes this ratio is not the same as the one that maximizes raw power density. It lies slightly higher, a delicate compromise between physical possibility and engineering practicality. In the tables accompanying these discussions, each number tells part of the story: ideal temperatures, comparative efficiencies, and power ratios for the leading candidate reactions. Together, they outline the vast scientific terrain between theory and realization. From the fierce brilliance of a nuclear test on a remote Pacific atoll, to the quiet hum of experimental plasma chambers in modern laboratories, humanity continues its search for controlled fusion, the art of holding a star within reach, but not letting it burn the hand that holds it. However, the actual ratio of fusion power to Bremsstrahlung radiation is almost certainly lower than early theoretical estimates suggest. The math, while elegant, often hides the messy realities of plasma behavior. It begins with a simple but idealized assumption that all the energy produced by fusion reactions ends up heating the fuel ions, which then pass that energy to electrons through collisions. Yet nature rarely cooperates with such clean models. In truth, fusion products move at much higher speeds than the ions that created them, and a large portion of their energy transfers directly to the electrons instead of the ions. This single deviation already distorts the expected power balance. Then there is the problem of impurities. The pure hydrogen isotope plasmas described in textbooks almost never exist in practice. Every real plasma contains trace amounts of other elements, tiny contaminants introduced by walls, magnetic coils, or even the materials used in diagnostics. These impurity ions radiate energy away, draining power and lowering the ratio of fusion output to Bremsstrahlung loss. And beyond impurities lie all the other, often ignored channels through which energy leaks out of a plasma: conduction, convection, and magnetic field instabilities that let heat escape long before it can be used. These effects are not independent, they interact. A confinement system that efficiently traps fusion products also tends to trap impurities and secondary radiation. A system that cleans itself quickly loses its stored energy. The engineer must strike a delicate balance. For every fusion reaction, the temperature that maximizes power output relative to Bremsstrahlung losses is always higher than the temperature that maximizes raw power density or minimizes confinement time. For deuterium-tritium fuel, the difference is manageable because Bremsstrahlung losses are small. But for advanced fuels like deuterium-deuterium, deuterium-helium-3, helium-3, helium-3, or proton-boron-11, the radiation losses become severe. They can reach levels that make net energy production impossible within a balanced quasi-neutral plasma. Many proposed solutions have come and gone, ideas to suppress radiation, to create anisotropic plasmas, or to separate ions and electrons in exotic ways. Each offers promise on paper, but collapses under experimental reality. Non-neutral or highly directional plasmas might avoid some of these limits, yet they bring their own formidable challenges in stability and control. The path forward is not merely to confine a plasma, but to confine it cleanly, stably, and at temperatures where fusion triumphs over radiation. In the classical picture of fusion, atomic nuclei are treated like rigid spheres. Each one carries a positive charge, and the repulsive Coulomb force keeps them apart. Only when two nuclei approach close enough for the strong nuclear force to take over can fusion occur. To visualize this, consider that the radius of an atomic nucleus is roughly 1 femtometer, a millionth of a billionth of a meter. For two hydrogen nuclei to collide at that distance, the required energy is enormous, far beyond what normal thermal motion could supply. A crude calculation suggests that the probability of fusion in such a scenario, based purely on classical physics, would be about 10 to the power of negative 290, essentially zero. The sun, then, should not shine at all. Yet it does. The reason lies in quantum mechanics. The quantum world allows for behavior that the classical world forbids. Nuclei are not point-like marbles, but fuzzy probability clouds, their edges blurred by the de Broglie wavelength. Quantum tunneling lets them slip through the Coulomb barrier instead of climbing over it. It is through tunneling that fusion occurs both in stars and in reactors on Earth. The rate of fusion depends on the cross-section, a measure of the likelihood that two particles will fuse when they collide. Because plasmas are not collections of identical particles but swarms of ions with a range of energies, scientists calculate an average fusion rate over a Maxwell-Boltzmann distribution, a statistical curve describing how particle energies spread around the plasma's temperature. These averaged values, measured and tabulated in laboratories, guide the design of every fusion experiment. Beyond the mechanics of fusion lies a deeper and stranger layer of physics, zero-point energy. Often abbreviated as ZPE, it represents the lowest possible energy a quantum system can possess. In classical physics, a system at its minimum energy would rest in perfect stillness. But quantum mechanics forbids absolute stillness. Even at absolute zero, the coldest conceivable temperature, atoms continue to vibrate faintly, jittering in place due to the Heisenberg uncertainty principle. The principle states that one cannot know both the position and momentum of a particle with perfect precision. If motion stopped entirely, both would be known exactly, which is impossible. Thus, even the void itself is never truly empty. Quantum field theory takes this idea further. It tells us that everything in the universe, from matter to light, arises from fields that permeate space. Electrons, quarks, and leptons come from matter fields. Photons, gluons, and other carriers of force emerge from force fields. Each of these fields is constantly fluctuating, never still, and each carries its own zero-point energy. The so-called vacuum of space is a seething ocean of invisible activity, a restless fabric of quantum fluctuations. Some physicists see this as a modern echo of the ancient concept of the ether, an all-pervading medium that fills the cosmos, not as a physical substance, but as an energetic foundation from which everything else arises. The challenge of fusion then sits between these worlds, the classical and the quantum, the practical and the profound. Engineers fight to contain plasma at hundreds of millions of degrees, while physicists study the quantum probabilities that make fusion possible in the first place. And as we continue to chase the dream of a star on Earth, we find ourselves reminded that even the emptiest vacuum, even the stillest space, hums with unseen energy, waiting, perhaps, to be understood. However, to avoid contradicting Einstein's theory of special relativity, this modern idea of an eth cannot be thought of as a tangible substance that we move through like air or water. Instead, it must be seen as an abstract background, an all-pervasive field woven into the very structure of space-time. Within this invisible fabric lies a concept that continues to intrigue and confound physicists: zero-point energy. Zero-point energy plays a central role in cosmology, the scientific study of the universe as a whole. But here lies a deep problem. Physicists still lack a complete and unified theory that explains how this mysterious energy fits within our broader understanding of the cosmos. The equations predict one thing, observation shows another. The theoretical amount of vacuum energy is enormous, while the actual energy we detect in the real universe is tiny. The gap between these two numbers is staggering, so large that it has been called the greatest mismatch in all of science. This puzzle is known as the cosmological constant problem. Einstein's general theory of relativity tells us that any form of energy, even the faint hum of vacuum energy, should affect the curvature of spacetime and thus influence gravity itself. And indeed, there is evidence that such an effect exists. The accelerating expansion of the universe suggests that some form of invisible energy, now called dark energy, is at work. The Casimir effect, where two metal plates in a vacuum experience a tiny measurable force pushing them together, provides further proof that the vacuum is not truly empty. These are clues, faint yet compelling, that energy lurks in the void. But why is its strength so small? One possible explanation is the delicate balancing act between the different quantum fields that make up the universe. Matter fields, composed of particles called fermions, may contribute negative energy, while force fields, composed of bosons, contribute positive energy. If these two components perfectly cancel each other out, the total would be zero. This elegant symmetry could, in theory, erase the vast energy predicted by quantum mechanics. However, such a balance would only occur if a principle called supersymmetry were exact. Supersymmetry proposes that every known particle has a hidden partner particle. Yet, despite years of searching with the Large Hadron Collider, the world's most powerful particle accelerator, no evidence of these partner particles has been found. If supersymmetry does exist, it seems to operate only at unimaginably high energy levels, far beyond the everyday world. The term zero-point energy originates from the German phrase Nullpunktsenergie, meaning energy at 0 point. Scientists also use related terms like ground state energy or zero-point radiation. When referring to the entire vacuum, they speak of the zero-point field, or ZPF. Depending on the context, this might mean the quantum electrodynamics QED vacuum, which governs light and electrons, or the quantum chromodynamics QCD vacuum, which deals with quarks and gluons. In both cases, what we think of as empty space is in fact a restless sea of invisible fields. In classical physics, particles possess kinetic energy from their motion and potential energy from their position. Temperature, for example, measures how fast particles are moving. At absolute zero, one might expect motion to cease entirely. Yet quantum physics refuses to let things rest. Even at this lowest possible temperature, particles retain a faint jitter, a remnant of their inherent uncertainty. This jitter is the zero-point energy. It can never vanish. The reason lies in the Heisenberg uncertainty principle, which states that you cannot know both the exact position and velocity of a particle at the same time. Because of this fundamental limit, quantum systems behave like tiny oscillators, always vibrating slightly. Even in their lowest energy state, known as the ground state, they continue to move. A striking example is liquid helium, which refuses to freeze at normal pressure no matter how cold it becomes. Its zero-point energy keeps its atoms in constant motion. Einstein's famous equation, E equals mass squared, shows that energy and mass are equivalent. This means that even a tiny amount of energy confined to a small region of space could, in principle, give rise to mass or particles. Quantum field theory, QFT, builds on this concept. It describes every point in space as a vibrating quantum field, with particles emerging as excitations, ripples, within these fields. Every field, from the electromagnetic to the gravitational, carries its own zero-point energy. Some experiments now suggest that particles themselves are not solid objects but disturbances in these invisible energy fields. Matter, as we perceive it, may simply be the visible trace of invisible fluctuations. This realization changes our view of nothingness. The vacuum is not empty, but dynamic, filled with potential and activity. Physicists often treat this background energy as constant, assuming it has little effect on calculations. Yet in general relativity, even a small amount of vacuum energy can shape the geometry of space-time. Its effects cannot be ignored. For decades, scientists hoped that some deeper law of nature would cancel out this infinite energy, rendering it harmless. They imagined that as the universe expanded, the vacuum energy would thin out, slowing cosmic growth. But in 1998, astronomers made a discovery that changed everything. Observations of distant supernova revealed that the universe's expansion is accelerating, not slowing down. Some mysterious energy within space itself is pushing galaxies apart. This phenomenon was named dark energy, and zero-point energy remains one of the most promising explanations for it, yet a great mystery remains. The amount of dark energy we observe is unimaginably smaller than what theory predicts, smaller by roughly 10 to the power of 120. This enormous discrepancy is why the cosmological constant problem continues to haunt physics. Somewhere in the quantum vacuum, the answer must lie hidden. Over the years, phenomena once thought purely theoretical have been confirmed through experiment. Spontaneous emission, in which atoms emit light seemingly at random, the Casimir force, a tiny attraction between close metal plates, the Lamb shift, a subtle change in electron energy levels, the magnetic moment of the electron, and Delbruck scattering, where light bends in the presence of atomic fields, all arise from quantum fluctuations of the vacuum. These are known as radiative corrections, small, measurable effects caused by interactions with virtual particles and fields that pop in and out of existence. In more complex areas such as quantum chromodynamics, zero-point energy becomes even more vital. It shapes how the strong nuclear force binds quarks inside protons and neutrons. It can create multiple stable states, break symmetries, generate chaotic dynamics, and give rise to new properties that emerge from the collective behavior of the fields themselves. These effects remind us that the vacuum is not a backdrop to physics, it is an active participant. So what once seemed like nothing is, in truth, everything. The space between galaxies, the silence between atoms, the void itself, all teem with unseen energy. The vacuum, far from being empty, may be the most important structure in existence. Within its restless motion, the ultimate secrets of the universe may still be waiting to be found. And yet, even now, scientists continue to pursue questions that reach into the deepest layers of reality. They study the strange relationship between zero-point energy and the ghostly realm of virtual particles, those fleeting entities that appear and vanish in the blink of a quantum instant. They probe the phenomenon of quantum entanglement, where particles remain mysteriously linked across vast distances, defying classical understanding. They ask whether inertial and gravitational mass, which seem identical in all our experiments, are truly the same. They question whether the speed of light, often treated as a universal constant, might ever vary under extreme conditions. And they wonder why the cosmological constant, the invisible hand steering the universe's expansion, has the value it does. This number influences how galaxies drift apart and how dark energy, a force that seems to make up most of the cosmos, operates. But the idea of zero-point energy didn't appear from thin air. It evolved from ancient speculations about what nothingness really meant. Long before quantum mechanics, the Greek philosopher Aristotle spoke of to keinon, meaning the empty. Yet he rejected the very concept of a vacuum, To him, nature abhorred emptiness. The universe, he argued, was filled with continuous substances, fire, air, earth, and water, that blended seamlessly without gaps or voids. In contrast, a rival school of thought, the atomists, led by thinkers like Democritus and Leucippus, imagined a universe composed of indivisible atoms moving through empty space. For them, the void was real. It wasn't just the absence of matter, it was the stage upon which existence unfolded. The tension between these two visions, continuity versus discreteness, would persist for centuries, confined largely to philosophical debate. Then came the Renaissance, when philosophy began to merge with experiment. In the mid-17th century, the German scientist Otto von Guericke built the first vacuum pump, a simple yet revolutionary device that could draw air out of a sealed chamber. For the first time, emptiness could be tested in a laboratory rather than merely imagined in the mind. Experiments showed that when air was removed, objects behaved differently. Bells could not ring, flames could not burn. To early scientists, it seemed they had created a true vacuum, a perfect void free from all substance. For a time, that was enough. The vacuum became the accepted picture of nothing. But as the 19th century drew to a close, new discoveries challenged that simplicity. Even when all gases were removed from a chamber, something still lingered: thermal radiation. Invisible heat, energy that refused to disappear. The idea that empty space was completely empty began to crumble. Physicists sought explanations. Many turned to the concept of the ether, an invisible medium thought to permeate all space. According to this view, the ether was not void at all. It was a delicate fabric that carried light and other forms of electromagnetic energy. James Clerk Maxwell's equations had shown that light behaved as a wave, and since all known waves required a medium, the ether seemed essential. Yet Maxwell himself admitted that this invisible substance was a convenient fiction, a mathematical placeholder for the unknown. Then came the pivotal Michelson-Morley experiment in 1887. With remarkable precision, it failed to detect any trace of the ether's motion. The result shocked the scientific community and cracked open the foundations of physics. In the wake of that discovery, Albert Einstein proposed his theory of special relativity, which elegantly eliminated the need for a stationary ether altogether. Space itself, Einstein argued, did not require a medium. Light could move through the vacuum because the vacuum was not truly nothing, but a fabric defined by its geometry and energy. From that moment on, the concept of emptiness became even more complicated. Scientists began to ask, could a truly empty space exist at all? If all matter and radiation were removed, and if the region were cooled to absolute zero, the coldest possible temperature where all motion theoretically stops, would anything remain? At first, the idea seemed sound: cool the vacuum enough, and perhaps you'd drain it of all energy. But as quantum theory matured, a new picture emerged. Even at absolute zero, the universe refused to be still. Tiny fluctuations rippled through the vacuum, creating pairs of virtual particles that blinked into existence and annihilated each other almost instantly. This restless undercurrent of energy was named zero-point energy. It was as if the cosmos itself could never rest, as if space were alive with invisible motion. What had once been called nothingness had become a seething ocean of potential, a place where particles could emerge from sheer possibility. Today, physicists see the vacuum not as an empty void, but as the most fundamental state of reality, brimming with invisible activity. Its energy might help explain why the universe expands, why particles behave as they do, and perhaps even how everything came to be. And so the questions continue. What is the true nature of the vacuum? Why does the zero-point energy exist at all? Could we ever tap into it? Each new experiment, from particle colliders to cosmic surveys, brings us a little closer to answers and reveals that what we call nothing may in fact be the most profound something of all. But in the 19th century, scientists lacked the instruments and the reach to dive into the frozen depths of absolute zero. Their laboratories were lit by gas lamps, their thermometers primitive, their imaginations straining against the limits of the possible. The question of what happens to energy at the coldest conceivable temperature remained open, mysterious, and unresolved. Could motion, vibration, and light themselves truly stop, or was there something still humming quietly beneath the silence? Then came the dawn of the 20th century, and with it a revolution in physics. In 1911, the German physicist Max Planck, already celebrated for his work in quantum theory, returned to a problem that had haunted him for more than a decade. In 1900, he had proposed that energy is not continuous, but delivered in discrete packets he called quanta. It was an elegant idea that helped explain how light is emitted and absorbed. But something in his original formulation didn't quite fit with the deeper laws of nature. As he re-examined his equations, Planck realized that even at absolute zero, when all motion should stop according to classical physics, energy could not vanish entirely. There would always remain a tiny, irreducible residue of energy. This became known as zero-point energy, the smallest possible vibration the universe allows. In 1912, Planck published another paper, refining his ideas. He described how radiation is emitted not as a steady flow, but as sudden bursts, each one linked to a specific frequency. Energy could be absorbed continuously, but it could only be released in fixed steps. This meant that even when a system was stripped of all heat, when it was colder than anything we can ever touch or measure, it still carried a faint echo of energy, a whisper from the universe's foundations. It was an idea that would slowly transform physics. By 1913, curiosity spread among scientists. Albert Einstein and his assistant Otto Stern sought to test whether this zero-point energy was real. They studied hydrogen gas, calculating its specific heat and comparing it with experimental data. At first, they thought their numbers confirmed Planck's prediction, but later, they found inconsistencies. Einstein eventually declared in a letter to a colleague that zero-point energy was dead as a doornail. Yet, like many scientific ideas before it, it refused to stay buried. In the following years, others took up the challenge. Peter Debye examined how zero-point motion in the atoms of a solid crystal could subtly alter X-ray diffraction patterns, even near absolute zero. Around 1916, the German chemist Walther Nernst proposed something even bolder, that the vacuum itself, what we once thought of as empty space, was filled with invisible electromagnetic energy. His claim suggested that emptiness might not be empty at all, but a sea of restless fluctuations. Einstein's later work on general relativity seemed to echo this possibility. The equations of his new theory hinted that even the vacuum could exert a measurable effect on the universe's expansion. Space itself could carry energy, influencing the grand cosmic motion of galaxies. The vacuum, once thought to be nothingness, was now seen as a player in the drama of existence. In the early 1920s, two researchers in Nernst's Berlin laboratory, Kurt Benowitz and Francis Simon, explored the melting behavior of materials at extremely low temperatures. By studying hydrogen, argon, and mercury, they uncovered evidence supporting the existence of zero-point energy. Their findings helped explain why helium, even under immense pressure and near absolute zero, stubbornly refused to solidify. A decade later, in 1934, Simon confirmed these predictions with remarkable precision. Meanwhile, in 1924, Robert Mulliken provided direct molecular proof. By comparing two versions of a boron-containing molecule, one built with lighter atoms and another with heavier ones, he found differences in their energy levels that could only exist if zero-point energy were real. The evidence was accumulating. What began as a mathematical curiosity was turning into physical truth. Then came a turning point. In 1925, Werner Heisenberg introduced matrix mechanics, a radically new framework for describing atomic behavior. It became one of the cornerstones of quantum mechanics. Within Heisenberg's equations, zero-point energy emerged naturally, as if woven into the very logic of the quantum world. But the mystery of atomic stability still loomed large. Since 1913, Niels Bohr had proposed his planetary model of the atom, electrons circling the nucleus in fixed orbits. It was a simple picture, and for a while it worked. Yet according to classical physics, any charged particle in motion should radiate energy and spiral inward, collapsing into the nucleus. If that were true, atoms, and everything made of them, should not exist. The British physicist James Hopwood Jeans pointed this out starkly in 1915. Classical theory, if taken literally, implied that the universe itself should collapse into nothingness. The paradox endured until 1926, when the Austrian physicist Erwin Schrödinger introduced his now famous wave equation. He showed that electrons do not behave like tiny planets, but like waves spread out around the nucleus. These waves cannot shrink to nothing because of quantum restrictions. Even at their lowest energy, electrons retain a small but finite amount of motion. This intrinsic vibration, the zero-point energy, prevents atoms from collapsing. It is, in a very literal sense, what keeps the material world standing. That same year, another physicist, Pascual Jordan, extended quantum theory further. He, along with Max Born and Werner Heisenberg, applied quantum rules not just to particles but to entire fields, such as the electromagnetic field, the force behind light and electricity. They imagined these fields as vibrating systems made of countless tiny oscillators. To their surprise, even when cooled to absolute zero, the total energy of these oscillators was infinite. The vacuum seemed to hold endless energy. Jordan was uneasy. He wrote to Einstein, suggesting this infinity might be a mathematical illusion, not a physical truth. By 1928, working with Wolfgang Pauli, Jordan found a way to handle this infinity, a process later called renormalization. It became one of the most essential tools in modern theoretical physics. Around this same period, in 1927, another mind, Paul Dirac, took quantum theory into a new realm. He created quantum electrodynamics, or QED, a theory describing how light and matter interact. In Dirac's equations, light could be both created and destroyed, absorbed and emitted. Crucially, he showed that spontaneous emission, the sudden release of light from an excited atom, depends on the ever-present zero-point energy of space. Even the most perfect vacuum, he explained, is not empty but alive with microscopic fluctuations. These invisible tremors of energy can spark the birth of light itself. 2 decades later, in the 1940s, the rapid progress of microwave technology made possible measurements of astonishing precision. Scientists observed the Lamb shift, a tiny difference in the energy levels of hydrogen atoms and the anomalous magnetic moment of the electron. These effects could not be explained without considering the subtle dance between matter and the restless energy of the vacuum. Physicists like Hans Bethe refined renormalization methods, originally hinted at by Hans Kramers and Victor Weisskopf, to bring the theory into alignment with experiment. The results confirmed that quantum electrodynamics was right and that zero-point fluctuations are a measurable feature of reality. Yet, even then, debate persisted. Some of the greatest minds, including Wolfgang Pauli, doubted that zero-point energy represented a true physical quantity. In his 1945 Nobel lecture, Pauli dismissed it as a mathematical artifact, an elegant fiction born of the equations. But others saw it differently. For them, the zero-point field was the quiet hum of existence itself, a subtle reminder that even in stillness, the universe is never truly at rest. From the gaslit laboratories of 19th century Europe to the high-energy accelerators of the 20th century, one thread has endured: the idea that energy can never entirely vanish. At every scale, from atoms to galaxies, there is always a residue, a vibration, a shimmer of life in what appears to be nothing. That is zero-point energy, the invisible heartbeat of the cosmos. But then, in 1948, something quietly extraordinary happened. A Dutch physicist named Hendrik Casimir, working in a time when the scars of war still shaped Europe's laboratories, made a discovery that would later echo through the foundations of quantum physics. Casimir found that 2 flat, uncharged metal plates, placed incredibly close together in a vacuum, would feel a subtle but measurable pull toward one another. It wasn't magnetism. It wasn't gravity. It was something stranger. This phenomenon became known as the Casimir effect, a force that arises not from matter itself, but from the restless fluctuations of zero-point energy, the ghostly energy of the vacuum that never entirely vanishes, even in what we call empty space. Casimir's insight didn't come out of nowhere. He had been studying colloids, dense suspensions like paint or mayonnaise, where tiny particles dance within thick fluids. The theory at the time, built on van der Waals forces, couldn't quite explain how these particles behaved. Casimir's colleague Theo Overbeek pointed out that the data and theory didn't line up. To understand why, Casimir teamed up with another Dutch physicist, Dirk Polder. Together, they refined the model and realized that a hidden factor had been overlooked. Light doesn't travel infinitely fast. It moves at a finite speed, and that delay, tiny though it may be, changes the rules. After discussing their puzzling results with Niels Bohr, Casimir connected their calculations to something deeper, the zero-point energy predicted by quantum mechanics. He wondered, if such forces could act between microscopic particles, might they also appear between two perfectly smooth mirrors facing each other in a vacuum? That question became the seed of his landmark prediction. The Casimir effect showed that even in total emptiness, quantum fluctuations can summon a real, measurable force. Nothing, it turned out, is not truly nothing at all. A few years later, in 1956, the Soviet physicist Evgeny Lifshitz expanded Casimir's theory to include a wide range of materials. He showed that both van der Waals and Casimir forces belong to a larger family of interactions called dispersion forces, subtle attractions that dominate at distances of about 1/10,000,000th of a meter. These forces play a hidden but crucial role in how materials behave at the smallest scales, from the structure of proteins to the design of nanoscale machinery. Zero-point energy was no longer just a curiosity. It became part of a much broader narrative, the realization that the vacuum itself is alive with activity. That idea found new support in 1951 when two American physicists, Herbert Callan and Theodore Welton, formulated the fluctuation dissipation theorem, often called FDT. Its roots went back to 1928 when Harry Nyquist, studying strange electrical noise in circuits, proposed that random fluctuations, what became known as Johnson noise, were tied to the way systems lose energy. FDT revealed a profound symmetry in nature. Whenever a system dissipates energy, losing it irreversibly as heat or radiation, there must also be a corresponding random motion or fluctuation within it. The two always go together. Loss and fluctuation are inseparable twins of the same physical law. This insight implied something radical. Even the vacuum could act like a heat bath, humming with microscopic vibrations. Perhaps, if one could understand those fluctuations deeply enough, it might be possible, at least in theory, to draw energy from the fabric of empty space. As experiments advanced, physicists confirmed that FDT holds true under quantum conditions, where the ordinary rules of classical physics no longer apply. These weren't just abstract equations anymore. They described real, measurable behavior. The empty space between atoms was becoming one of the most active players in modern science. By 1963, researchers were taking these ideas further. The Jaynes-Cummings model, a cornerstone of quantum optics, was introduced to describe what happens when a simple atom interacts with a confined field of light inside an optical cavity, essentially two mirrors trapping photons between them. What they found was astonishing. An atom could emit or absorb light in ways that depended on the cavity itself. This environment didn't just host the atom, it changed its behavior. Spontaneous emission, once thought to be an intrinsic property of atoms, could be modified, accelerated, or even suppressed. During the 1970s, experiments confirmed this surprising prediction. By placing atoms near reflective surfaces, scientists could literally control how often those atoms released photons. At first, it seemed impossible. How could an atom sense its surroundings if it can only interact with them by emitting light? Yet the data was clear. These effects gave rise to an entirely new field called cavity quantum electrodynamics, or CQE. It showed that mirrors and cavities can alter the basic rules governing how matter and light exchange energy. This discovery, predicted in 1946 by Purcell and now known as the Purcell effect, linked directly back to the same vacuum forces Casimir had revealed decades earlier. The deeper scientists looked, the more they realized that the vacuum isn't a static void. It's a restless ocean. Even in its lowest possible energy state, a quantum system can never be perfectly still. This is where zero-point energy truly comes into focus. The Heisenberg uncertainty principle states that one cannot simultaneously know a particle's exact position and velocity. If a particle were ever completely at rest, both would be precisely defined, which quantum mechanics forbids. Therefore, every particle must always retain a residual irreducible motion. That jitter, the smallest possible vibration, is what we call zero-point energy. To make this more tangible, physicists often use the analogy of a quantum harmonic oscillator. Imagine a particle attached to a spring, bouncing back and forth. Even when it seems to have settled at the bottom of its potential well, quantum mechanics ensures it never stops moving entirely. This eternal oscillation gives rise to the equation that defines zero-point energy. E equals sec 2, where ka h bar is Planck's constant divided by 2 times pi, and wo, omega, represents the angular frequency of the system's vibration. Sometimes systems have multiple ground states, different configurations with the same lowest energy. This property is called degeneracy. It arises from symmetries in nature, where certain transformations leave a system's energy unchanged. According to the third law of thermodynamics, as a system approaches absolute zero, it settles into its ground state. The entropy, the measure of disorder, depends on how many such states exist. A perfect crystal with only one possible ground state reaches zero entropy at absolute zero. But systems with degeneracy retain a trace of disorder, a fingerprint of their hidden symmetries. From Casimir's metal plates to the restless vacuum beneath all of existence, this story reveals something extraordinary. Even when the universe seems still, it is never truly at rest. Every atom, every field, every patch of space carries within it an invisible tremor, a whisper of energy that can never be silenced. What we call nothing is, in truth, one of the most dynamic and mysterious realms in all of physics, a place where silence hums and emptiness itself exerts a force. But some systems can have negative temperatures and still reach extremely excited states. This strange situation defies our everyday intuition about heat and energy. In a sense, it means the system is hotter than infinite, a counterintuitive regime where adding energy can actually make it more ordered instead of more chaotic. These rare cases exist only under very specific conditions, like in certain magnetic materials or highly controlled atomic systems, where the normal rules of thermodynamics bend in remarkable ways. And now we move into the world of quantum field theory, or QFT. This is not just another branch of physics. It is the language that describes everything, from the smallest particles to the grandest cosmic forces. In this framework, the universe is not built from tiny billiard balls or hard particles flying through space. Instead, everything is made of continuous fields, vibrating, fluctuating sheets of energy that stretch across all of space and time. Even what we call empty space isn't truly empty. Quantum field theory reveals that the vacuum itself is alive with activity. Imagine an invisible ocean filled with an infinite number of tiny oscillators, each one quivering, trembling, and contributing its own minimum energy, what physicists call the zero-point energy. These are like the smallest possible versions of those spring-like systems we study in classical mechanics, only now they exist at every point in space. According to QFT, the universe is built from 3 main families of fields. The first are matter fields. These form everything we can touch and see. Electrons, quarks, and other fundamental particles are excitations, or ripples, in these matter fields. Their basic units are called fermions. The second are force fields. These are the messengers that carry interactions between particles. Photons carry the electromagnetic force, giving rise to light and electricity. Gluons transmit the strong nuclear force, the one that binds quarks together inside protons and neutrons. Each force field is carried by a particle known as a boson. Then there is the Higgs field, a mysterious field that fills the entire universe and endows particles with mass. Its corresponding quantum particle is the Higgs boson, discovered in 2012 at CERN's Large Hadron Collider, confirming one of the great predictions of modern physics. All these fields have a zero-point energy. The lowest possible energy state of any field is called its zero-point field, or ZPF. So when we talk about the vacuum, we're not talking about nothingness. We're talking about a seething, bubbling sea of invisible fields, each fluctuating around its lowest energy level. This restless energy of the vacuum itself is known as vacuum energy. Physicists describe the average value of a field in this vacuum as its vacuum expectation value, or VV. It tells us what the field looks like when we strip away all particles and disturbances. And depending on the kind of field, the nature of this vacuum can vary. For instance, the QED vacuum governs electromagnetic interactions, those between photons and electrons, while the QCD vacuum manages the strong force that binds quarks inside atomic nuclei. Each of these vacuums has its own structure, its own subtle fingerprint on reality. Recent research has hinted at something astonishing, that particles themselves may not truly be things at all, but merely ripples in this underlying quantum ocean. Everything we call matter, every atom, every molecule, every bit of solid material, may simply be energy waves rising and falling in this endless sea of fields. But here's where the strangeness deepens. When you sum up the energy of every single point in space using the quantum formula E equals h multiplied by omega divided by 2, you get an infinite amount of energy contained in any small region. Infinity, packed into a teaspoon of empty space. Obviously, that cannot be right in practical terms. So physicists developed a mathematical technique called renormalization to subtract the infinities and yield finite, meaningful results. Yet, even with this adjustment, scientists still disagree on how much energy the vacuum truly holds. Quantum mechanics suggests that the vacuum should contain an enormous amount of hidden energy, enough to make empty space blaze with unimaginable intensity. Paul Dirac, one of the founders of quantum theory, once described this as a vast sea of energy, an unseen ocean of activity beneath everything. But general relativity, Einstein's theory of gravity, tells a different story. If the vacuum really had so much energy, the gravitational curvature of space would be enormous, and the universe would not look as it does. The galaxies would bend and twist far more than we observe. Somehow, the vacuum energy predicted by quantum theory and the vacuum energy required by relativity differ by an almost inconceivable factor. Some estimates say by about 1, followed by 120 zeros. This is known as the cosmological constant problem, one of the deepest puzzles in physics. To understand this discrepancy, we look to the Heisenberg uncertainty principle. This principle states that certain properties, like energy and time, cannot both be known with perfect precision. In other words, the universe allows temporary violations of energy conservation. Energy can appear out of nowhere for very short moments, as long as it vanishes quickly enough. These brief bursts of energy flicker in and out of existence, giving rise to what physicists call quantum fluctuations. Because of these fluctuations, the vacuum is not static, it's dynamic. It constantly births and annihilates pairs of virtual particles that momentarily pop into existence before disappearing again. Even though these events are fleeting, their effects are measurable. They slightly shift the energy levels of atoms, bend light, and even cause forces between neutral plates in experiments known as the Casimir effect. In certain formulations of quantum theory, such as quantum perturbation theory, these vacuum fluctuations influence the properties of real particles, their mass, their behavior, even their charge. In the diagrams physicists use to describe particle interactions, called Feynman diagrams, these effects appear as loops, circles that represent the influence of the zero-point energy on the interaction. The electromagnetic field, the one responsible for light, was the first to be studied in quantum terms. In the 19th century, James Clerk Maxwell described it beautifully through his equations, which unified electricity, magnetism, and light into one coherent theory. But in the 20th century, those classical equations were upgraded by quantum mechanics into a new, more precise framework called quantum electrodynamics, or enkelkstyret. However, this shortcut does not solve everything. Even when physicists attempt to erase the zero-point energy from the equations, it refuses to vanish. It reappears, woven back into the mathematics as if reality itself insists on keeping it there. When we use the Heisenberg equations to describe how quantum fields evolve over time, the vacuum field, the field that remains even in perfect emptiness, must be included in the solution. Without it, the logical machinery of quantum theory collapses. The vacuum field enforces the rules of commutation, those subtle mathematical relations that tell us how physical quantities like position and momentum can coexist. So, zero-point energy is not a minor technicality or a removable term. It is part of the foundation on which quantum field theory stands. From this point, two essential questions arise. First, is zero-point energy truly infinite, or is it merely unimaginably large? When scientists try to calculate or measure this energy in a confined region, such as a perfectly sealed box that reflects all electromagnetic waves, they immediately encounter limits. The highest energy waves cannot be contained unless the walls are flawless, something nature never provides. Since no material is perfectly reflecting, these extreme waves escape, and we are forced to impose an upper limit on the calculation. This artificial limit is known as a cutoff. It prevents the mathematics from running to infinity and allows the theory to give finite answers that can match experiment. Expanding this concept from a box to the scale of the universe creates deeper complications. General relativity, which tells us that energy and mass curve the fabric of spacetime, must also be considered. Theoretical physicist John Wheeler once proposed the idea of geons, localized waves of energy that warp spacetime yet cannot be fully confined because their own gravitational pull distorts their container. In this context, a cutoff again becomes necessary. Without it, the calculated energy density would rise so high that it would warp space beyond recognition, folding the universe into itself. The very act of trying to quantify vacuum energy threatens to reshape the geometry of the cosmos. This leads to the second major question. Does zero-point energy have real consequences in the physical world? In most laboratory calculations, scientists often disregard it since physics usually deals with energy differences, not absolute totals. If every energy level is shifted by the same constant amount, measurements of change remain unaffected. Yet this simplification breaks down when gravity enters the picture. According to Einstein's general relativity, energy determines curvature. More energy means more bending of spacetime. Here, the absolute amount matters. It cannot be dismissed as a mere offset. The vacuum energy, if truly immense, could act as a cosmological force, influencing the shape and expansion of the universe. Evidence that zero-point energy is physically real comes from measurable effects. The Casimir effect, for instance, arises when two metal plates placed close together in a vacuum experience a minute but definite attraction. This happens because the quantum fluctuations between the plates are slightly different from those outside them, creating a pressure imbalance. Similarly, the Lamb shift, an observed shift in the energy levels of electrons in hydrogen atoms, and the anomalous magnetic moment of the electron both reveal the subtle fingerprints of vacuum energy. These phenomena confirm that the vacuum is not a silent void but a restless sea of fluctuations. Among the various vacua theorized by physicists, one stands out as particularly complex: the quantum chromodynamics (QCD) vacuum. QCD describes the strong nuclear force that binds quarks into protons and neutrons. Unlike the electromagnetic vacuum, which can be thought of as relatively simple, the QCD vacuum is filled with dynamic energy structures known as condensates. These include the gluon condensate and the quark condensate, patterns of fluctuating energy that define the confined phase of quark matter. Within this regime, quarks are trapped so tightly that they can never exist freely, only as parts of larger particles. The force carriers responsible for this confinement are gluons, particles that carry a type of charge called color. Unlike photons, which are neutral, gluons interact with each other as well as with quarks, making the mathematics of QCD intensely nonlinear and vastly more complicated than that of quantum electrodynamics, QED, the theory of light and electromagnetism. At the heart of the standard model of particle physics lies another remarkable field, the Higgs field. It is distinct because it does not vanish even in its lowest energy state. Its potential resembles a Mexican hat, flat around the top with a circular valley at the bottom. The lowest energy point is not at the center but around the rim. When the universe cooled below a critical temperature in its early moments, the Higgs field chose a position in that valley, breaking a fundamental symmetry. This event, called spontaneous symmetry breaking, gave rise to mass. Through interactions known as Yukawa couplings, the components of the Higgs field endow particles like electrons and quarks with mass, while gauge bosons, force-carrying particles, also gain mass through their coupling with the scalar field. The strength of the Higgs field has been measured to be about 246 giga-electron-volts per the speed of light squared, the only dimensional parameter in the standard model. The Higgs mechanism has a striking analogy to superconductivity. In a superconductor, electrons pair up and move without resistance through a material cooled to extremely low temperatures. The electromagnetic field inside such a material cannot propagate freely. It is screened by the condensate of electron pairs. Similarly, in the vacuum of space, the Higgs field plays the role of a medium that screens certain forces and gives others mass. Space itself can be viewed as a kind of quantum medium, alive with invisible structure even when it appears perfectly empty. All of this brings us back to zero-point energy. It is the irreducible energy that remains even when every particle is at its lowest possible state. It cannot be eliminated by subtracting constants or redefining baselines. Its influence shows up in experiments and in the behavior of the universe itself. In general relativity, this vacuum energy contributes to what Einstein called the cosmological constant, a term he originally introduced to make the universe static, but later described as his greatest blunder. Yet today, the cosmological constant is again at the center of cosmology, linked to dark energy and the accelerating expansion of the universe. Thus, zero-point energy is not a mere curiosity in the equations of physics. It is a hidden reservoir of power built into reality itself. From the structure of atoms to the curvature of space, from the confinement of quarks to the birth of mass, its presence is felt. The vacuum, far from being nothing, is a dynamic, restless ocean, a stage on which the universe itself performs. However, when physicists try to calculate the expected value of what is called zero-point energy, the restless quantum energy that exists even in the emptiest regions of space, they find something shocking. The predicted value is not just slightly off from what we observe in the universe, it is larger by about 120 orders of magnitude. That's a number so vast, it defies intuition. If the observed vacuum energy were compared to a single drop of water, the theoretical prediction would be an ocean that stretches beyond the visible universe. This staggering mismatch has a name: the cosmological constant problem. It remains one of the most persistent and perplexing mysteries in all of physics, sitting at the crossroads of quantum mechanics, relativity, and cosmology. The concept of zero-point energy is not just theoretical abstraction. It manifests in the physical world through an extraordinary phenomenon known as the Casimir effect, named after the Dutch physicist Hendrik Casimir, who proposed it in 1948. Casimir suggested that when two metal plates are placed very close together, just a few nanometers apart, they would experience a faint but measurable attraction. The cause, he explained, lies in the vacuum itself. Empty space is not truly empty. It's alive with fluctuations, waves of every possible wavelength flickering in and out of existence. However, between the plates, some of these waves cannot fit. As the plates move closer, more wavelengths are excluded, reducing the vacuum energy between them. The imbalance of energy between the inside and outside creates a subtle push that drives the plates together. In the early 1950s, experiments hinted that Casimir's prediction was correct, though the data came with large uncertainties. For decades, the effect remained a tantalizing idea more than a confirmed reality. Then, in 1997, Steve Lamoureux performed a precise experiment that left little doubt. The Casimir force was real. His results ignited a wave of new research, and over the following years, multiple experiments confirmed the effect beyond dispute. By 2009, a team led by Jeremy Munday and Federico Capasso demonstrated something even stranger. Under specific conditions, such as when the plates were placed in a carefully chosen liquid, the Casimir force could become repulsive. Suddenly, what had always been an invisible pull could transform into a quantum push. The implications were profound. If physicists could harness this effect, they might one day design systems where microscopic components levitate without touching, eliminating friction altogether. This idea inspired visions of nanoscale machines and quantum levitation devices gliding through fluids on cushions of fluctuating vacuum energy. The Casimir effect also inspired theoretical extensions. One of the more intriguing is known as the Scharnhorst effect. It suggests that between two closely spaced conducting plates, light might travel ever so slightly faster than its usual speed limit. Though this remains purely theoretical, it serves as a reminder that the vacuum, once thought of as nothingness, has hidden properties that challenge even Einstein's understanding of spacetime. Zero-point energy does not only influence empty space between plates, it also leaves its fingerprint on the tiniest building blocks of matter. One of the first experimental clues came from what is known as the Lamb shift. In the mid-20th century, physicist Willis Lamb discovered that certain energy levels of hydrogen atoms were slightly different from what quantum mechanics predicted. The difference was small, about 4.38 millionths of an electron volt, but it was undeniable. The explanation lay in the quantum fluctuations of the vacuum. Virtual particles flickering around the atom momentarily altered the way its electron interacted with the electromagnetic field. In effect, the vacuum behaved like a medium with its own dielectric properties, subtly reshaping atomic structure. When similar experiments were carried out on muonic atoms, atoms in which a muon replaces the electron, the effects became even more pronounced. The heavier muon orbits closer to the nucleus, where the electromagnetic fields are vastly stronger. Here, vacuum fluctuations no longer act as a minor correction. They become a dominant part of the system's behavior. These studies suggest that even the very definition of empty space depends on the energy fields and particles inhabiting it, visible or not. The deeper physicists probed, the more extraordinary the implications became. It appeared that energy from electromagnetic radiation, light itself, could transform into matter, and matter could dissolve back into pure energy. This concept lies at the core of quantum electrodynamics, or QED, the theory describing how light and charged particles interact. QED revealed that even the simplest electromagnetic interactions are not simple at all. They are layered with corrections, feedback loops, and momentary flashes of virtual particles that pop in and out of existence faster than we can measure. In extremely strong electromagnetic fields, these effects become nonlinear. The equations of classical electromagnetism no longer suffice. The vacuum begins to behave like a strange material with its own optical properties. It can polarize light, bend it, or even change its speed, something that Einstein's theory of relativity would normally forbid. This regime, known as the Schwinger limit, marks the point at which the vacuum itself can produce real particles out of nothing but energy. These predictions trace back to the work of Werner Heisenberg and Hans Heinrich Euler in 1936, and independently Victor Weisskopf in the same year. They proposed that the vacuum is not static, but influenced by the fields and particles within it. Later theorists refined the idea, showing that strong magnetic or electric fields could alter the energy density of space itself. This meant that nothingness had physical properties, and those properties could change. According to Einstein's principle of Lorentz invariance, the laws of physics should look the same to all observers moving at constant speeds. Light, in particular, should always travel at the same speed in a vacuum. But if the vacuum is not uniform, if its energy fluctuates or interacts with magnetic fields, then this symmetry might not hold perfectly. Some modern theories of quantum gravity predict that Lorentz invariance could break down at extremely high energies, allowing the speed of light to vary slightly depending on its direction or polarization. In 2017, a team led by astronomer Roberto Mignani from the National Institute for Astrophysics in Milan reported evidence hinting at such an effect. Observing the light from RX J1856, 5 Ms 3754, the nearest known neutron star to Earth, they found that the visible light from the star was polarized by about 16%, far higher than the 1% expected from ordinary interstellar gas. The results suggested that the light's polarization had been altered as it passed through the star's intense magnetic field, a possible sign of vacuum birefringence, one of the predicted nonlinear effects of quantum electrodynamics. Mignani noted that when Einstein developed general relativity a century earlier, he could not have imagined it guiding GPS satellites. Likewise, the consequences of this discovery may take decades to unfold. Further observations, especially at X-ray wavelengths, could strengthen the case, though current telescopes are not yet sensitive enough. Future missions, such as China's Hard X-ray Modulation Telescope and NASA's Imaging X-ray Polarimetry Explorer, may finally provide confirmation. While quantum effects reveal the restless structure of the vacuum on microscopic scales, cosmological observations have shown something equally astonishing on the largest scales. In the late 1990s, astronomers discovered that distant supernovae appeared dimmer than expected, implying that the expansion of the universe was accelerating. This contradicted all prior expectations and led scientists to resurrect an old idea, Einstein's cosmological constant. Once thought to be zero, it might actually have a small but positive value. That would mean even the emptiest regions of space contain energy, a mysterious force now known as dark energy. The nature of dark energy remains one of the greatest open questions in science. It accounts for roughly 70% of the total energy content of the universe, yet its origin is unknown. One possibility is that it arises from the same zero-point energy that causes the Casimir effect, the Lamb shift, and vacuum polarization. If so, then the smallest fluctuations of the quantum vacuum and the vast expansion of the cosmos are connected by the same unseen force. Bridging that gap between the infinitesimal and the infinite may be the key to uniting quantum theory and general relativity, two of the most successful yet fundamentally incompatible frameworks in physics. The search continues, across laboratories and galaxies alike, to understand whether the vacuum is truly empty, or whether it is, in fact, the most energetic entity in existence. However, this estimate is famously wrong by about 120 orders of magnitude. It is one of the greatest mismatches in all of physics. To explore why, the European Space Agency launched the Euclid telescope on July 1st, 2023. Its mission: to chart galaxies stretching up to 10 billion light-years away and uncover how dark energy has shaped the cosmos. By mapping how distant galaxies cluster and distort over cosmic time, scientists hope to learn whether dark energy has remained constant or evolved as the universe aged. If dark energy changes, it may support a concept known as quintessence, a theory suggesting that cosmic acceleration arises not from a fixed cosmological constant, but from a dynamic scalar field permeating space. In this view, dark energy behaves more like a shifting fluid than a steady pressure. Although no evidence yet confirms quintessence, it remains a tantalizing possibility. If proven true, it would mean that the universe's expansion should slow down slightly more than predicted by a simple cosmological constant. Testing this theory requires precision on an almost unimaginable scale. Some researchers propose that signs of quintessence might appear as tiny violations of Einstein's equivalence principle, the cornerstone of general relativity that insists the laws of physics are identical everywhere. Others suggest we might detect slow drifts in the fundamental constants of nature. Subtle changes in quantities like the speed of light or the strength of gravity over vast stretches of time or space. Scalar fields are not new ideas. They appear both in the standard model of particle physics and in string theory, yet they bring their own complications. The same vacuum fluctuations that make the cosmological constant problem so severe also predict that scalar fields should gain enormous masses from zero-point energy, energy that exists even in the absence of particles. This problem echoes through multiple layers of modern physics. Cosmic inflation, a brief but explosive episode right after the Big Bang, may hold some of the answers. During that fraction of a second, the universe expanded faster than the speed of light, ironing out irregularities and seeding the vast structure of galaxies we see today. Quantum fluctuations of the vacuum during this period, minute ripples in energy, are believed to have stretched to cosmic scales, forming the seeds of stars, galaxies, and clusters. Inflation helps explain why the universe looks uniform in all directions, why the cosmic microwave background is evenly spread, why the universe appears flat, and why exotic relics like magnetic monopoles never emerged in abundance. Still, the cause of inflation itself remains unknown. It mimics the behavior of dark energy, but is far more intense and fleeting. Some physicists think both phenomena might stem from the same origin, the vacuum energy of space. Quantum fluctuations, microscopic, spontaneous jitters in the fabric of reality, may have powered both inflation in the past and dark energy in the present. There are even theories that inflation might have played a role in baryogenesis, the mysterious imbalance between matter and antimatter that allowed the universe to exist at all. In this picture, quantum processes during inflation tip the scales, producing slightly more matter than antimatter. Yet this remains uncertain, one of the deepest unsolved puzzles in cosmology. Physicist Paul S. Wesson once posed a provocative question: what if zero-point energy, the lowest possible energy of a quantum system, is real and has measurable effects? When he tried to include it in general relativity, difficulties emerged. Einstein's equations suggest that this energy should not gravitate, it cannot behave like light or radiation. That contradiction has driven decades of debate. Scientists have long argued about whether zero-point fluctuations are physically real or merely a mathematical convenience. Julian Schwinger, one of the founders of quantum electrodynamics, QED, tried to rebuild the theory without relying on fluctuating vacuums. His source theory described interactions through physical sources rather than empty space trembling with energy. Using this framework, Schwinger offered an alternative explanation for the Casimir effect, the subtle attraction between two uncharged metal plates in a vacuum. First published in 1975 for simple fields and expanded in 1978 to electromagnetic ones, his model showed that such forces could arise even without invoking vacuum fluctuations. Later, in 2005, Robert Jaffe advanced a similar argument. He maintained that zero-point fluctuations are a powerful mathematical tool, but not a physical necessity. In contrast, researchers like Milani demonstrated that vacuum fields are indispensable for keeping quantum electrodynamics mathematically consistent with observation. The debate persists. Is zero-point energy a genuine physical field or simply a calculation trick? Despite the uncertainty, zero-point energy remains central to all attempts at unifying the forces of nature. It is embedded in every successful quantum field theory. Yet, as Jaffe emphasized, no experiment, not even the Casimir effect, has conclusively proved that vacuum energy exists as a tangible entity. Classical electromagnetism, quantum electrodynamics, and the Standard Model still treat the electromagnetic vacuum as a smooth, linear system with no measurable self-interaction. Even so, certain quantum effects challenge that simplicity. The Casimir effect, the Lamb shift in hydrogen atoms, and other delicate phenomena could, in principle, be explained through mechanisms that do not require a restless vacuum. But higher symmetry theories, which extend beyond the familiar U1 gauge symmetry of electromagnetism, paint a more dynamic picture. In these models, the vacuum behaves like a virtual plasma, turbulent, structured, and full of potential. It can host vortices, entangled states, and other features that blur the boundary between energy and matter. Experimental hints support this richer view. Phenomena such as the Aharonov-Bohm effect, the Josephson effect, and the quantum Hall effect all suggest that electromagnetic fields are not mere abstractions. They possess real physical influence, even in regions where classical fields should vanish. Such behavior hints that electromagnetism may operate through a more intricate system, perhaps an SU2 or higher gauge theory, where nonlinearity, multiple stable configurations, and even chaotic behavior could emerge naturally. From the cosmic scale of galaxies to the microscopic scale of neurons, nature seems to organize itself around energy flow. Every system, living or not, contributes to the grand increase of entropy across the universe. The human body remarkably dissipates energy about 10,000 times more efficiently per unit of mass than the sun. Complex structures, it seems, evolve precisely to accelerate the universe's drive toward equilibrium. This theme leads back to zero-point energy once again. In recent years, researchers have turned to quantum phase transitions, changes of state that occur at absolute zero temperature. At that limit, thermal motion disappears and only quantum fluctuations remain. These fluctuations, born of zero-point energy, can cause entire materials to reorganize their structure. One striking example is superconductivity. Superconductors, materials that conduct electricity with perfect efficiency, are governed by quantum principles from the ground up. Their electromagnetic behavior is described by the London equations, which link electric and magnetic fields in a tightly bound quantum relationship. Within them, zero-point fluctuations help stabilize a state where resistance vanishes entirely. What emerges is a glimpse of how deeply quantum energy defines the workings of the universe, from the emptiest vacuum to the densest matter. However, some scientists have long questioned whether the mathematical framework that defines quantum mechanics might in fact be rooted in purely classical physics. Could the strange probabilistic equations that govern the behavior of subatomic particles actually emerge from principles that predate quantum theory itself? This question sits at the intersection of two grand traditions in physics: the classical, which seeks order through determinism, and the quantum, which finds truth in uncertainty. Physicist Winston Bostick was one of those who dared to blur this boundary. He argued that the London equations, fundamental relations describing how superconductors expel magnetic fields, might not require quantum theory at all. According to him, these equations could just as easily arise from classical models, particularly those involving plasma systems. In his experiments, he observed entities called Beltrami vortices, tightly wound helical flows of plasma that seem to mirror the filament-like magnetic flux tubes found in Type II superconductors. These similarities were not superficial. They hinted that the ordered states seen in superconductivity might emerge from collective classical processes, not quantum behavior. Other thinkers, such as Herbert Froelich, extended this argument further. Froelich proposed that when the equations for compressible fluids are combined with the London equations, they can describe the bulk properties of superconductors without invoking wave functions, Planck's constant, or any other explicitly quantum parameters. In this interpretation, the difference between plasma vortices and superconducting currents is one of scale, not principle. Both systems organize energy into coherent, self-sustaining patterns that resist entropy. This organization arises because a vortex, unlike random thermal motion, channels energy into structured motion. As these vortices form, the system undergoes a kind of phase transition, an abrupt shift from disorder to order, without any increase in temperature. Such transitions demonstrate that energy can reorganize itself into stable configurations purely through internal dynamics. The result is a system that possesses multiple stable energy states, a property reminiscent of what quantum physicists call zero-point energy. From this perspective, the divide between the classical and quantum worlds begins to blur. The ordered dynamics of classical systems might influence, or even determine, what we perceive as quantum effects. The birth of a Beltrami vortex, some have noted, resembles the spontaneous appearance of virtual particles in a quantum vacuum, a fleeting exchange of energy between existence and nothingness. This connection leads to a profound cosmological question. If vacuum energy can occupy multiple stable states, could this explain the origin of the universe itself? Many cosmologists believe that during the earliest moments after the Big Bang, fluctuations in vacuum energy drove an event known as cosmic inflation, a rapid exponential expansion that set the initial conditions for galaxies, stars, and eventually life. Without this imbalance, the universe might have collapsed into equilibrium, uniform, unchanging, and devoid of complexity. Expansion created gradients, differences in energy density that fueled the formation of structure. These gradients are essential to life and motion. Even today, Earth avoids thermodynamic equilibrium because it constantly receives energy from the sun. The sun, in turn, burns through its own supply of fuel thanks to the gravitational imbalances left over from cosmic inflation. In this way, every living system, every weather pattern, and every electrical spark can trace its energy lineage back to the vacuum fluctuations of the early universe. Vacuum energy, then, may be the architect of order. But can humanity ever harness this hidden reservoir? The notion of tapping zero-point energy has fascinated and frustrated scientists for more than a century. In the late 19th century, long before quantum theory, Nikola Tesla speculated that empty space was not truly empty. He believed it contained an all-pervading medium, an ether, from which limitless energy could be drawn. Though the concept of the ether was later discarded, the dream of extracting energy from the vacuum persisted. Since Tesla's time, countless inventors and theorists have claimed to find ways to exploit zero-point energy, often facing skepticism and accusations of pseudoscience. Still, the idea refuses to vanish. In recent decades, it has resurfaced not only in fringe research, but also in advanced scientific programs. Defense agencies and private aerospace firms in the United States have quietly funded studies into vacuum energy manipulation. Similar projects have appeared in China, Germany, Russia, and Brazil. The central phenomenon of interest is the Casimir effect, a subtle force that arises between two uncharged metal plates placed very close together in a vacuum. Caused by quantum fluctuations, the effect demonstrates that even empty space contains measurable energy. Most physicists dismiss the Casimir force as impractical for energy generation. The plates naturally attract each other, and separating them again requires more energy than the force provides. However, in 1984, physicist Robert Forward proposed a theoretical design for a vacuum fluctuation battery. His model suggested that by dynamically controlling the electrical charge between the plates, one might cyclically recharge and extract work from vacuum fluctuations. In 1999, NASA researcher Harold Pinto went a step further. Writing in Physical Review, he described a thought experiment for a Casimir engine. claiming that continuous extraction of energy might be possible under certain conditions. Pinto argued that if no alternative explanation could account for the observed behavior, such a system could lead to the creation of endless pollution-free energy. Yet critics such as Garrett Model from the University of Colorado countered that the Casimir force is conservative. It stores and releases energy symmetrically, making net extraction impossible. Even if one could harvest energy briefly, the process would always cost as much or more to reset. Despite these challenges, research persisted. In 2008, DARPA launched the Casimir Effect Enhancement (CEE) program, calling for proposals to explore new ways to manipulate quantum vacuum forces. That same year, Model and colleague Garrett Hush patented a device that aimed to draw power from zero-point fluctuations using gas flowing through a precisely engineered Casimir cavity. By 2012, preliminary experiments hinted at unexplained excess energy, but the results were inconclusive. Whether the source was truly vacuum energy or an artifact of measurement remains unknown. The roots of this inquiry stretch back even further. In 1951, Callan and Welton formalized the fluctuation dissipation theorem, expanding on earlier work by Harry Nyquist in 1928. This theorem explained the mysterious electrical noise known as Johnson noise, revealing that every system that loses energy to its surroundings also experiences compensating fluctuations. In other words, dissipation and fluctuation are inseparable, two sides of the same physical process. This realization implied that even the vacuum, if treated as a kind of thermal reservoir, could in principle exchange energy with matter. Across the 20th and 21st centuries, such insights have continued to challenge the boundary between what is considered classical, quantum, or speculative. The idea that the vacuum itself is not empty, but a seething ocean of potential energy remains both controversial and alluring. Whether humanity will ever learn to control that ocean, or whether the effort will forever remain theoretical, depends on discoveries yet to come. For now, the vacuum hums quietly, everywhere and nowhere, holding secrets that still elude the reach of human technology. However, not everyone agrees with this idea. In the early 1960s, a debate began that would echo through decades of physics and philosophy. Two scientists, McDonald and Harris, stood firmly against the notion that energy could be drawn from zero-point fluctuations, the restless quantum tremors that persist even in absolute emptiness. They argued that the fluctuation dissipation theorem, or FDT, could not be true if such extraction was impossible. To them, nature's balance was too perfect, too constrained by thermodynamic law to allow something for nothing. Then, in the 1980s, the discussion was reignited. Researchers Grau and Klein, and later Klein alone in 1986, examined the strange hum of Johnson noise, the random motion of electrons in a resistor connected to an antenna. They concluded that this noise should obey the same rules as thermal radiation described decades earlier by Max Planck. That connection implied something profound. If temperature dropped to absolute zero, all noise would vanish. No heat, no motion, no signal. And if that were true, the FDT would collapse, leaving a gap in one of the pillars of modern physics. By 1988, a new voice entered the conversation. Physicist Kiss suggested that the zero-point term might be a mathematical ghost, a bookkeeping error rather than a window into hidden energy. He compared it to the infinities that plague quantum electrodynamics, where equations explode into meaninglessness until tamed by renormalization. Later, in 1996, Abbott and his collaborators proposed a more nuanced interpretation. They accepted that zero-point energy might be infinite, but insisted that fluctuations themselves could remain measurable and finite. It was a compromise between philosophy and physics, a way to keep the equations useful without claiming the impossible. Despite the theoretical conflict, experiments continued. Over the years, evidence accumulated that FDT could indeed hold under certain quantum conditions. Subatomic particles behaved as if they danced to a hidden rhythm, drawing and dissipating energy in ways that classical thermodynamics could not explain. The concept that zero-point fluctuations could influence systems that lose energy, tiny, delicate systems balanced at the edge of equilibrium, slowly gained credibility. In 2000, physicists Amon Alvarian and Theo Neuwenhuizen took a bold step further. Their study proposed that zero-point energy could, in theory, perform useful work. By exploiting quantum properties, they described a system that could extract energy from a single heat bath without violating thermodynamic laws. The process did not break physics, it simply used the strange loopholes of the quantum world. Following their lead, other researchers explored even stranger possibilities. That under specific quantum conditions, classical thermodynamic limits, such as the Carnot cycle's efficiency ceiling, might be surpassed by leveraging negative entropy, a kind of order borrowed from the quantum vacuum itself. Yet the mystery deepened. The boundary between quantum mechanics and thermodynamics remained one of the most puzzling questions in science. How could the probabilistic world of quantum particles reshape the rigid energy boundaries of classical physics? Could the universe's smallest fluctuations rewrite the laws that govern stars and engines alike? Scientists did not have the answer then, and they still do not. And when it comes to the dream of using zero-point energy for space travel, the discussion moves from the laboratory to the edge of imagination. The idea remains speculative, viewed with skepticism by mainstream physicists. There is still no unified theory of quantum gravity, no complete framework connecting the fabric of space-time with the quantum vacuum. Without it, any link between zero-point energy and gravity remains conjecture. A few speculative papers have hinted that zero-point energy might affect gravity, perhaps through forms of shielding or repulsion, but evidence is absent. Einstein's general theory of relativity, however, offers an interesting parallel. It predicts that rotating masses create a subtle force known as the gravitomagnetic interaction. This effect, dependent on the rate of spin, can in rare conditions produce repulsion rather than attraction. In neutron stars, some scientists believe this might lead to a gravitational Meissner effect, analogous to the magnetic behavior of superconductors. The force, though, is unimaginably weak, far beyond any practical use. In 1963, physicist and aerospace engineer Robert Forward proposed that within general relativity, certain configurations could yield anti-gravitational effects. If every atom has spin, he reasoned, then materials composed of differently aligned spins might produce varying gravitational properties. He speculated that materials designed to enhance time-varying gravitational fields could, in theory, create a toroidal or donut-shaped gravitational field opposing normal gravity. Much like how an iron core amplifies an electromagnetic transformer, this hypothetical structure could manipulate gravity itself. 3 years later, in 1966, another scientist, Ditt, explored how superconductors might interact with gravity. He showed that these materials experience fluxoid quantization, a key concept linking magnetic and gravitational effects on the quantum scale. The research hinted at a bridge between quantum mechanics and relativity, though the connection remained incomplete. Fast forward to 1993, when Shanho and Barton made a striking discovery. They found that light seemed to travel faster when confined between two Casimir plates, thin, closely spaced metallic surfaces where vacuum fluctuations are suppressed. The phenomenon implied the existence of negative energy, suggesting that the vacuum itself could influence the speed of light. This result fit neatly into the growing body of theories about exotic matter, materials with negative energy density that could theoretically create wormholes, shortcuts through space-time capable of faster-than-light travel. Such matter, if real, might share properties with dark energy, the mysterious force accelerating the universe's expansion. In 1992, physicist Ivany Podkletnov published a paper that would ignite worldwide debate. He claimed that a certain kind of rotating superconductor could shield against gravity. Around the same time, between 1991 and 1993, Ning Li and Douglas Torr published a series of studies suggesting that superconductors might generate measurable gravitomagnetic effects. They proposed that the arrangement of atomic spins within the material could produce a gravitational magnetic field, and that a changing magnetic field could induce a gravitational electric field. Their third paper described this dual interaction as evidence of a link between electromagnetism and gravity itself. The scientific community was divided. Some doubted the magnitude of the effects, others found the results intriguing enough to pursue. In 1997, Ning Li attempted to replicate Podkletnov's experiments but found the effect too small to measure, or perhaps non-existent. 2 years later, in 1999, she left the University of Alabama to found her own research company, AC Gravity LLC. In 2001, AC Gravity received a research grant of roughly $448,000 from the U.S. Department of Defense to continue its anti-gravity investigations. The project sparked interest across aerospace and defense sectors. Yet, by 2002, when the funding period ended, no public findings emerged. That same year, Boeing's Advanced Research Division, Phantom Works, reached out to Ivany Podkletnov, seeking collaboration on gravity-related experiments. The trail ends there, at least publicly. What came of those conversations is unclear. But from the quiet hum of zero-point fluctuations to the bold dream of gravity control, the quest continues. A reminder that even in the emptiness of space, the universe may still be alive with untapped energy waiting to be understood. However, due to strict restrictions on the transfer of Russian aerospace technology, the project soon found itself tangled in geopolitical red tape. Lieutenant General George Melner, then head of Boeing Phantom Works, confirmed that the company's efforts to collaborate with the Russian physicist Podkletnov were blocked by Moscow. He admitted, however, that the scientific ideas at the core of Kletnov's work could not be dismissed outright. The principles appear sound, Melner said in a recorded statement. They don't violate known physical laws. The question is whether those laws can be engineered into something that actually works. That tension between theoretical possibility and practical realization became a recurring theme. In 2002, two American researchers, Froing and Roach, built upon the work of earlier scientists such as Put-Hush and Alubier. Using high-performance computer simulations, they modeled how a spacecraft similar to Alubier's proposed design might interact with what is called the zero-point field, the lowest possible energy state of the quantum vacuum. This field, invisible and constant, fills all of space. Their virtual experiments explored how the vacuum could exert a measurable force on a craft, comparing theoretical thrust values to predictions derived from quantum field dynamics. Their results were striking. They suggested that the exotic form of negative energy required for Alubier's model would work most efficiently with a saucer-shaped vehicle surrounded by complex electromagnetic fields. These fields, they believed, could bend or distort the surrounding vacuum itself, effectively altering the geometry of space. In theory, such distortions could reduce local inertia and allow a craft to surf the quantum foam. Then in 2009, a new and ambitious idea emerged from Italian researchers Gio Fontana and Bernd Binda. They proposed a model that could potentially tap into the zero-point energy through interactions with nuclear and electromagnetic fields in the form of gravitational waves. Their work drew inspiration from Linus Pauling's atomic nucleus model, which includes pairs of tightly bound particles called deuterons. These subatomic pairs, according to Fontana and Binda, might act as sources of gravitational waves at extraordinarily high frequencies, comparable to X-rays and gamma rays. They theorized that the rapid motion of these deuterons inside the nucleus could generate gravitational disturbances. Though general relativity provides a strong understanding of gravitational waves, it is not a quantum theory, and Fontana and Binda's concept bridged this gap in a novel way. They argued that unstable atomic species, linked to the vacuum's zero-point fluctuations, might emit gravitational waves under certain conditions. So far, this remains a hypothesis untested in laboratories, awaiting technology sensitive enough to detect such faint high-frequency ripples in space-time. 5 years later, in 2014, NASA's EagleWorks laboratories reignited the discussion with a bold announcement. They had constructed and tested a device known as a quantum vacuum plasma thruster, often shortened to Q-thruster. The propulsion system appeared to generate thrust without any propellant, using principles related to the Casimir effect. This effect, a well-documented quantum phenomenon, arises when two metal plates placed very close together in a vacuum experience a measurable force caused by fluctuations of the vacuum energy itself. By 2016, EagleWorks had published a peer-reviewed scientific paper describing their tests, a significant milestone. The researchers proposed that the zero-point field could behave like a pilot wave, and that thrust might occur because particles interacted asymmetrically with the quantum vacuum. They carefully identified 9 possible sources of error, such as air currents, electromagnetic interference, or heat differentials. But the fact that independent scientists reviewed the data marked an important step toward legitimacy. The results did not prove that quantum vacuum propulsion was real, but they made it worth further investigation. The story of humanity's effort to harness unseen energy does not end there. Long before quantum physics, humans learned to draw power from another invisible force, heat from the Earth itself. Geothermal energy, originating deep within the planet, is one of the oldest energy sources used by civilization. It combines residual heat from Earth's formation with the ongoing decay of radioactive elements in the crust and mantle. Evidence shows that people have used natural hot springs for more than 10,000 years. Archaeological sites from the Paleolithic era reveal bathing areas fed by geothermal vents. The Romans later perfected this practice, constructing elaborate bathhouses heated by subterranean water. In the city now known as Bath, England, they transformed a Celtic spring into a vast spa complex, charging visitors a fee, possibly the first commercial use of geothermal power. By the 1500s, the French town of Chaudes Egg had established the world's first district heating system powered by hot groundwater. A few centuries later, in 1827, Italian engineers in Lardarello began using geothermal steam to extract boric acid from volcanic mud. That marked the first industrial use of the planet's heat. Innovation accelerated in the 19th and early 20th centuries. In 1892, the city of Boise, Idaho, installed the first U.S. district heating system using geothermal water, later copied by Klamath Falls, Oregon. By 1907, the Hot Lake Hotel in Oregon was fully heated using geothermal sources, and in 1930, an inventor named Charles Lee built the first downhole heat exchanger to warm his home directly from the earth. Iceland and Tuscany followed similar paths, channeling steam to greenhouses and homes. Electricity generation from geothermal power began in dramatic fashion. On July 4, 1904, Prince Piero Ginori Conti tested a small turbine at Lardarello, Italy, successfully lighting 4 bulbs. By 1911, the first commercial geothermal power plant was operating at the same site. It remained the world's only geothermal facility until 1958, when New Zealand constructed its own. The Lardarello complex expanded rapidly, reaching 594 megawatts of output by 2012. The technology spread worldwide. In 1960, California's Geysers Field became the site of the first American geothermal power station. Its original turbine, producing 11 megawatts, ran for more than 3 decades. In 1967, the Soviet Union introduced the first binary cycle power system, using organic fluids to capture energy from lower temperature sources. The U.S. adopted the design in 1981, making it possible to generate electricity from fluids as cool as 81 degrees Celsius. Later, in 2006, a plant in Alaska began producing power from geothermal water at only 57 degrees Celsius, a record low. The Earth's internal heat is vast. Scientists estimate the total thermal energy at roughly 1,031 joules, or 3 times 10 to the power of 15 terawatt-hours. About 20% of this comes from the planet's initial formation, while the rest is maintained by radioactive decay from elements like uranium, thorium, and potassium. Deep drilling projects have revealed just how potent these sources are. In Cornwall, England, a borehole more than 5 kilometers deep struck granite rich in thorium, producing intense heat. Inside the Earth, pressures and temperatures rise so high that solid rock behaves like a slow-flowing liquid. At the boundary between the core and mantle, temperatures exceed 4,000 degrees Celsius. Globally, the Earth releases about 44 terawatts of heat to its surface, replenished continuously by radioactive decay at about 30 terawatts. This is more than twice humanity's total current energy consumption, though much of it cannot be captured. On average, temperature increases by roughly 25 to 30 degrees Celsius per kilometer of depth, a rate known as the geothermal gradient. Near tectonic boundaries, this gradient is far higher, making those regions ideal for power generation. By 2010, estimates of potential geothermal electricity output ranged from a modest 35 gigawatts to more than 2 terawatts, depending on how much nations were willing to invest in deep drilling. Wells reaching 10 kilometers into the crust could unlock even larger reserves. By 2019, the global installed capacity had reached about 15.5 gigawatts, with the United States alone providing nearly 1/4 of that total. Geothermal energy remains one of the cleanest and most reliable power sources available. A typical plant emits about 45 grams of carbon dioxide per kilowatt hour, less than 5% of what a coal plant produces. And unlike wind or solar, geothermal stations operate continuously day and night, unaffected by clouds or seasons. Today, countries such as Iceland, Kenya, the Philippines, El Salvador, and New Zealand derive a substantial portion of their electricity from geothermal fields. Beneath their surfaces, ancient forces continue to burn, steady, silent, and constant. While humanity dreams of harnessing the quantum vacuum and the energy of the stars, the Earth itself still offers a reminder. Power is already here, waiting below our feet. However, thanks to the accelerating march of modern technology, geothermal energy has broken through the limits that once confined it to a handful of volcanic regions. The invention of binary cycle power plants, coupled with refined drill techniques, has unlocked a new chapter in human interaction with the Earth's internal heat. Once, geothermal stations were tied only to the most geologically active zones, places where steam naturally vented from the crust. Today, they are beginning to appear in landscapes far more ordinary, from gentle European plains to the arid deserts of Australia. Across the globe, experimental sites are reshaping our understanding of what's possible. In Landau and Insheim, Germany, binary systems quietly convert the hidden warmth of the deep earth into electricity. In France, the Salt Soufar project demonstrates how controlled subsurface engineering can turn dormant heat into steady carbon-free energy. Not every venture has gone smoothly. In Basel, Switzerland, one ambitious project was shut down after small earthquakes were triggered by deep injection activities. Yet even in failure, lessons have been learned, refining the science of how to extract power safely from below our feet. Beyond Europe, a new generation of demonstration projects is emerging in countries such as Australia, the United Kingdom, and the United States. Each installation acts as both a laboratory and a beacon, proving that geothermal energy is not confined to tectonic hot zones, but is, in principle, a resource available nearly everywhere. In Myanmar, surveys have identified over 39 promising geothermal sites, including several near the bustling city of Yangon. The Earth, it seems, has more warmth to offer than humanity has yet learned to use. The concept of harnessing the Earth's heat is ancient. Long before electricity, humans used geothermal sources to bathe, cook, and heat their homes. Archaeological evidence traces such uses back to the Paleolithic era. What began as a simple act, settling near hot springs for comfort, has evolved into a global industry. By 2004, about 70 countries were using geothermal energy directly, producing a total of roughly 270 petajoules of heat. 3 years later, geothermal heating provided around 28 gigawatts of power, enough to supply approximately 0.07% of the world's energy needs. Modest, perhaps, but its efficiency is unmatched, since it requires no conversion from one form of energy to another. The warmth flows naturally, needing only pipes and pumps. Seasonal cycles shape its rhythm. During warmer months, geothermal heating plants often run below full capacity, conserving output for winter when demand peaks. Even ground that feels cold to the touch hides energy within. 6 meters, about 20 feet below the surface, the temperature remains stable year-round. Ground source heat pumps can access this constant heat reservoir, quietly moving warmth into homes during winter and reversing the process to provide cooling in summer. At the core of geothermal electricity generation lie hydrothermal systems, natural reservoirs of hot water or steam sealed beneath the surface. These systems are divided into two main categories: vapor-dominated and liquid-dominated. The legendary geothermal fields of Lardarello in Italy and the geysers in California belong to the vapor-dominated class, producing superheated steam at temperatures ranging from 240 to 300 degrees Celsius. More common, however, are liquid-dominated systems, often found near volcanic arcs or rift zones around the Pacific. These can exceed 200 degrees Celsius and power large-scale flash plants, where pressurized steam drives turbines before being cooled and re-injected underground. Most geothermal wells generate between 2 and 10 megawatts of electricity. After the steam has done its work, the cooled water is sent back into the earth, a closed cycle that sustains the resource. By 2013, the world's largest liquid-dominated geothermal system was operating in Cerro Prieto, Mexico. There, underground temperatures soar to 350 degrees Celsius, driving turbines that collectively generate about 750 megawatts of power, enough to supply hundreds of thousands of homes. In lower temperature systems, where water ranges from 120 to 200 degrees Celsius, engineers must pump it to the surface. Such conditions often occur in regions where heat rises through deep faults, like parts of the western United States and Turkey. In these settings, binary cycle power plants, based on the Rankine cycle, come into play. These facilities use a heat exchanger to transfer energy from the hot geothermal fluid to an organic working fluid, which vaporizes at a low temperature and turns a turbine. Binary plants first appeared in the Soviet Union during the late 1960s and remain one of the cleanest technologies available, producing no harmful emissions. Not all geothermal systems occur naturally. Engineers have learned to create their own through a process known as engineered geothermal systems, or EGS. In places where rock is hot but dry or lacks natural fractures, they drill deep wells and inject water at high pressure. This fractures the rock, forming channels through which water can flow, heat up, and be returned to the surface. The method bears some similarity to hydraulic fracturing used in oil and gas extraction, but avoids the toxic chemicals associated with that industry. Instead, particles of sand or ceramic are used to keep the cracks open, maintaining the system's permeability. Directional drilling further expands the potential of these reservoirs, allowing engineers to reach heat zones from a single well pad. Small-scale EGS projects in France's Alsace region and Germany's Rhine Valley, at sites such as Soultz-sous-Forez, Landau, and Insheim, are already feeding electricity into local grids. Another approach, known as closed-loop or advanced geothermal systems, eliminates direct contact with subsurface fluids altogether. Instead, sealed pipes circulate a working fluid deep underground, absorbing heat and returning it to the surface. This method sidesteps many of geothermal's natural limitations: no need for permeable rock, no fluid loss, and no risk of contamination. A Canadian company, Ever, has tested such a closed-loop design in Alberta. Although the region's geothermal gradient proved insufficient for electricity generation, the pilot system still produced around 11,000 megawatt-hours of thermal energy in its first 2 years of operation. The concept demonstrates that even modest heat can be useful when captured efficiently. Like wind and solar power, geothermal energy boasts low operating costs once built, but the upfront expenses remain significant. Drilling is the largest financial challenge. In Nevada, for example, a single pair of geothermal wells, one for extraction and one for reinjection, costs about $10 million. Together, they may generate roughly 4.5 megawatts of electricity. Yet, because about 20% of wells fail to yield adequate heat or flow, the average cost of a successful well can climb to around $50 million. Part of this expense comes from the geology itself. Unlike oil and gas fields, which are usually found in softer sedimentary rocks, geothermal reservoirs lie deep within igneous or metamorphic formations, dense, unyielding, and costly to penetrate. Still, as drilling technologies advance, these costs continue to fall. The same innovations that revolutionized the oil and gas industry, directional drilling, advanced sensors, and predictive modeling, are now being repurposed to tap the steady, silent heat of the planet. And so, kilometer by kilometer, the human species is learning to reach deeper, not for fuel to burn, but for warmth that has burned beneath our feet since the world began. And deep beneath our feet, the Earth's crust conceals both promise and peril. When engineers drill into geothermal reservoirs, they are not entering a uniform, predictable world. The rocks themselves are fractured, riddled with stress lines that cause vibrations strong enough to damage drilling tools. Inside these fractures lie abrasive minerals such as quartz grinding against metal as the drill descends. Corrosive fluids eat away at the machinery, and temperatures that can exceed several hundred degrees Celsius threaten to destroy the sensitive electronics that guide the operation. To survive in such conditions, geothermal wells must be encased in steel and cement from top to bottom, a protective layer designed to endure shifting temperatures and pressures. In contrast, oil and gas wells are usually cemented only near their base. Geothermal wells are also wider, requiring more material and precision during construction. Each meter drilled is a battle against geology itself. Between 2013 and 2020, the landscape of renewable energy investment was dominated by private capital. Roughly 3/4 of all renewable energy funding came from private investors seeking both returns and responsibility. But not all renewables attracted equal attention. In 2020, geothermal energy drew only about 1/3 of its investment from private sources. Investors often see geothermal development as riskier and slower to yield profit compared to wind or solar projects, which are easier to scale and faster to build. Yet this cautious perception may be changing. In January 2024, the Energy Sector Management Assistance Program, known as SMAP, published a landmark report titled Socioeconomic Impacts of Geothermal Energy Development. It described geothermal energy as a hidden powerhouse of opportunity. According to the report, every megawatt of geothermal capacity can create around 34 jobs, more than double the employment impact of wind or solar power. These are not just temporary construction jobs. They range from engineering and drilling to education, community planning, and maintenance. Many include on-site training, giving local workers new technical skills and pathways into stable careers. The report also emphasized community integration. Geothermal projects often work side by side with local governments to improve infrastructure, build roads, provide vocational training, and establish revenue-sharing programs. These collaborations bring electricity and heat to remote regions while supporting agriculture through stable power for irrigation and food processing. Moreover, geothermal initiatives are increasingly designed with gender equality and inclusion in mind. Programs provide scholarships, apprenticeships, and employment for women and underrepresented groups, ensuring that the economic benefits of geothermal energy reach the entire community. Together, these initiatives contribute to stronger local economies, higher government revenues, and lasting social gains, such as better health, improved education, and more resilient societies. Still, geothermal development is a high-risk endeavor. The process unfolds in multiple stages: exploration, geophysical surveying, drilling, testing, and finally, full production. Many projects fail before commercial viability is proven. Early stages rely heavily on equity financing because traditional loans are too rigid for the uncertainties involved. One recurring technical challenge arises in areas rich in carbonate rock. As hot fluids circulate through these formations, they dissolve minerals such as calcium carbonate. When the fluids rise and cool, these minerals precipitate, forming a hard, stone-like buildup called calcite scaling. The result is reduced fluid flow, mechanical wear, and eventual shutdowns for maintenance. Despite these obstacles, geothermal energy remains one of the most sustainable energy sources on the planet. The amount of heat extracted from the Earth is infinitesimal compared to its total heat content, about 100 billion times greater than all human energy use in 2010. The planet is cooling very slowly on a geological timescale, and geothermal extraction does not accelerate that process. Moreover, geothermal systems recycle their working fluids. The extracted water is reinjected into the ground to be reheated and reused, creating a near-closed loop of energy recovery. In many regions, using energy directly from the Earth instead of relying on material resources has sharply reduced humanity's environmental footprint. Iceland stands as a powerful example. Its geothermal fields generate electricity and provide enough heat to warm homes, greenhouses, and even city sidewalks. In Reykjavik, snow melts without the need for chemical salts, yet local effects still matter. Over decades, continuous extraction can lower underground temperatures and water levels. Historic geothermal sites like Larderello in Italy and the geysers in California have experienced declining output as their reservoirs cooled. By reducing production rates and re-injecting water, operators have managed to restore some of their capacity and prolong the lifetime of these fields. Consider the Wairakei Power Station in New Zealand. When it began operating in November 1958, it represented a triumph of geothermal engineering. Its output peaked at 173 megawatts in 1965, but by then the supply of high-pressure steam had already begun to fall. In 1982, production dropped to 157 megawatts. 2 decades later, engineers added 2 isopentane systems, boosting capacity by about 14 megawatts. Although some records were lost after organizational changes, the lessons learned at YRK shaped modern geothermal management. Sustainability depends on careful balance between extraction and reinjection. However, geothermal fluids are not pure. They often carry gases such as carbon dioxide, hydrogen sulfide, methane, and ammonia. If released unchecked, these emissions can contribute to global warming, acid rain, or unpleasant odors. On average, geothermal plants emit about 122 kilograms of carbon dioxide for each megawatt hour of electricity, far below fossil fuel levels, but still measurable. Some plants, particularly those in Turkey, emit more pollutants than gas-fired plants during their early years. To counter this, modern facilities employ emission control systems and closed-loop technologies. New methods, such as the closed-loop designs developed by companies like Ever, promise to reduce emissions to zero by isolating fluids from the environment entirely. The fluids also contain trace elements, mercury, arsenic, boron, and antimony, that can pose risks if released. Reinjection practices now prevent most of these substances from entering the biosphere. In addition, engineers must monitor geological stability. In some geothermal fields, land subsidence has been observed as underground pressure decreases. In others, like Staufen in Germany, uplift has occurred due to chemical reactions underground. There, an anhydrite layer transformed into gypsum after contact with water, doubling its volume and pushing the ground upward. Enhanced geothermal systems, which rely on hydraulic fracturing to improve permeability, can also induce earthquakes. A notable example occurred in Basel, Switzerland, where water injection triggered over 10,000 seismic events in just 6 days, some measuring up to magnitude 3.4 on the Richter scale. The project was halted, highlighting the need for strict monitoring and adaptive regulation. Yet in terms of resource efficiency, geothermal power remains one of the least intrusive energy technologies. Producing 1 gigawatt of electricity requires only about 3.5 square kilometers of land, compared to 32 for coal and 12 for wind farms. Water use is minimal too, roughly 20 liters per megawatt hour, while coal, nuclear, and oil plants consume more than 1,000 liters. The physical footprint is small, but the energy runs deep. And as we move from geothermal energy into the realm of theory, another fascinating idea emerges: perpetual motion. It refers to the concept of an object moving endlessly without external input, a dream pursued for centuries. The idea of a perpetual motion machine, one that performs work forever without consuming energy, violates the fundamental laws of thermodynamics. The first and second laws dictate that energy cannot be created from nothing, and that every process increases entropy, the measure of disorder in a system. These rules apply universally, from subatomic particles to galaxies. The apparent endless motion of planets, stars, and moons might seem like perpetual motion, but even these celestial giants are gradually losing energy. Solar wind, gravitational radiation, and drag from interstellar particles all act to slow them down, however imperceptibly. No natural system runs forever without loss. Machines powered by tides or ocean currents, though renewable, still draw energy from sources that will one day fade. The sun itself will burn out in roughly 5 billion years. In 2016, scientists discovered an unusual form of matter called a time crystal. On a microscopic scale, its atoms oscillate in a repeating pattern without consuming energy. This phenomenon fits the literal description of perpetual motion, yet it does not violate thermodynamic principles. Time crystals exist in their quantum ground state, which means they cannot do work or release energy. They move, but their motion is purely structural, a property of their atomic arrangement rather than a usable process. The pursuit of perpetual motion has a long history, from medieval inventors sketching wheels with hidden weights to modern tinkerers building magnetic rotors. Countless attempts have been made to defy thermodynamics. Each failed, reinforcing the same conclusion: motion without energy input is impossible. The laws that govern the cosmos are immutable, and every real system eventually runs down. What remains is not disappointment, but insight, the understanding that true sustainability lies not in endless motion, but in intelligent balance between what we take and what we return. In the deep heat of the earth and the delicate motion of atoms, Humanity finds two extremes of energy science. One shows how we can responsibly harvest the planet's internal warmth. The other reveals the limits of our imagination. Both remind us that energy, in all its forms, obeys the same universal truths. And yet, even today, a few inventors still chase the ancient dream of endless energy. They no longer call their creations perpetual motion machines, at least not openly. The phrase has become too controversial, too stigmatized by centuries of failed experiments. Instead, they speak of over-unity devices, a softer name for the same impossible goal, producing more energy than one consumes. But beneath the new terminology, the question remains unchanged. Can energy truly be created from nothing? Modern physics answers decisively, no. Every credible scientist agrees that perpetual motion, when attempted within a closed system, violates at least one of the laws of thermodynamics. These laws are not arbitrary human inventions. They are careful summaries of how nature behaves, tested through countless experiments and verified by every working machine on Earth. The first law, often called the law of conservation of energy, declares that energy cannot be created or destroyed. It can only change form. A flame turns chemical energy into heat and light. A turbine turns kinetic energy into electricity. Nothing emerges from nowhere. The total amount of energy in a closed system always remains constant. The second law is subtler but equally relentless. It states that energy naturally flows from concentrated to dispersed states. Heat moves from hot to cold, never the reverse. Every process increases the total disorder or entropy of the universe. This law tells us that no engine, no matter how cleverly designed, can be perfectly efficient. The idealized Carnot engine defines the upper limit of efficiency between two temperatures, and even it falls short of perfection. Real engines perform far worse, losing energy to friction, turbulence, and the inevitable spread of heat into the environment. Because of these principles, the efficiency of any real machine can never exceed 100%. The power output of a heat engine is always less than the thermal energy it consumes. Some of that energy is forever lost as waste heat, dissipating into the surroundings. Even devices that convert mechanical motion into electricity, like generators, must surrender some portion of their energy to resistance, vibration, or friction. Absolute efficiency, like absolute zero temperature, remains a theoretical boundary we can only approach but never reach. Still, deceptive examples appear. Some small devices, such as certain clocks or low-power gadgets, seem to operate endlessly without visible energy input. In reality, they draw on subtle environmental changes, variations in air pressure, temperature, or humidity between day and night. Others harness steady but finite natural sources like ocean currents or atmospheric movement. They seem to run forever, but only as long as the external energy supply continues. Once that supply ceases, the illusion of perpetual motion collapses. Scientists classify perpetual motion machines according to which thermodynamic law they violate. A first-kind machine supposedly creates energy from nothing, directly breaking the law of conservation of energy. A second-kind machine would convert ambient heat into mechanical work without any cooler reservoir, something the second law forbids. A third-kind machine imagines eliminating all friction and resistive losses, allowing motion to persist forever due to inertia alone. But in reality, no system is perfectly isolated, and no material is free of dissipation. Every moving object, no matter how well engineered, eventually slows. In scientific terms, such perpetual motion is not just technically difficult, but epistemically impossible. That means it cannot occur under our present understanding of physics. To overturn it would require rewriting the deepest principles of the natural world. The conservation of energy is not just a rule of convenience, it is mathematically rooted in the very symmetry of nature. In 1915, mathematician Emmy Noether proved that every conservation law corresponds to a fundamental symmetry. For energy, that symmetry is time invariance. The idea that the laws of physics are the same today as they were yesterday and will remain the same tomorrow. If energy could spontaneously appear or vanish, that symmetry would break, and the entire structure of physics would need rebuilding from the ground up. Physicists have tested this assumption across the observable universe. By examining the light from distant stars and galaxies, scientists compare the behavior of matter now with how it behaved billions of years ago. Techniques such as spectroscopy, analyzing the wavelengths of starlight, reveal that atomic transitions, chemical reactions, and physical constants have remained nearly unchanged through cosmic history. The conclusion is clear. The laws of physics, including the laws of thermodynamics, have held firm for as long as the universe has been visible to us. Because of this, when someone presents a design for a perpetual motion machine, physicists do not consider it a challenge to the laws of nature. They see it as a misunderstanding of those laws. The real difficulty is not in disproving the design, it's in explaining exactly where it fails. Every new attempt becomes an opportunity to revisit fundamental principles and sharpen our understanding of energy, entropy, and equilibrium. Some of these thought experiments have become famous. In 1900, physicist Gabriel Lippmann imagined a mechanism known as the Brownian ratchet, a tiny device that could, in theory, harness the random motion of molecules to produce useful work forever. For 12 years, it remained an open question. Then in 1912, Marian Smoluchowski demonstrated that the ratchet would not function as imagined because the same molecular randomness would also affect the mechanism itself, preventing any net gain of energy. The ratchet failed, but the insight it brought deepened our grasp of statistical mechanics. Historians have traced humanity's fascination with perpetual motion back centuries. In the mid-19th century, Henry Dirks published a comprehensive history of failed attempts, offering a blunt critique of those who persisted in seeking the impossible. Even earlier, in 1670, John Wilkins, Bishop of Chester and member of the Royal Society, outlined 3 supposed sources for perpetual motion: chemical reactions, magnetic forces, and gravity itself. His ideas inspired generations of inventors. Magnets, in particular, have held a special allure. They seem to move objects without visible effort, to push and pull without contact. Wilkins proposed a device where a magnet at the top of a ramp would draw a metal ball upward, then allow it to drop through a small hole back to the bottom, ready to climb again. The concept was elegant, intuitive, and entirely wrong. Gravity and magnetism would cancel each other out before any perpetual cycle could begin. Yet this simple design has been copied, reimagined, and redrawn countless times over the centuries. The story of perpetual motion is not really about defying physics. It's about human imagination confronting its limits. Each failure illuminates a deeper truth about how energy flows and how the universe resists our desire for endless motion. In that sense, the dream of the over-unity machine serves a purpose after all. It reminds us that while the laws of thermodynamics cannot be broken, our curiosity about them never truly stops. However, if the magnet is strong enough to pull the ball up the ramp, it is not weak enough to let gravity pull the ball through the hole. That simple conflict, one force overpowering the other, illustrates a fundamental problem that has haunted inventors for centuries. Modern designs try to bypass this dilemma with elaborate arrays of ramps and magnets, transferring the ball from one magnetic field to another, hoping to maintain motion forever. Yet, despite centuries of ingenuity, the underlying issue remains unchanged. Both magnetism and gravity act at a distance, and neither provides limitless energy. Gravity is a quiet sculptor of motion. It draws a dropped object toward the ground, transforming potential energy into kinetic energy. But before that fall can occur, energy must be added, lifting the object in the first place. This input-output relationship is unbreakable. No matter how cleverly arranged, every system leaks energy through friction, heat, or air resistance. There are no free rides in physics. One of the earliest attempts to defy this rule dates back to the 12th century with the invention of Bhaskara's wheel. It featured a circular frame lined with weighted arms, designed so that as the wheel rotated, the weights on one side would extend outward, while those on the opposite side retracted. The asymmetry was meant to create a constant imbalance, forcing the wheel to spin endlessly. In practice, the illusion vanished quickly. The torque from the extended weights was canceled by their reduced number, and the wheel came to rest, another early casualty in the long war against entropy. Other inventors turned to magnetism. They envisioned levitating rotors and frictionless bearings, objects suspended by invisible fields, forever spinning in midair. The idea sounds perfect. No contact, no friction, but perfection here is deceptive. A floating object may spin freely, but it cannot perform useful work without interacting with something else. The instant it does, friction returns. Even if one could create a near-perfect vacuum to minimize drag, atomic-level imperfections and slow material degradation would eventually bring the motion to a halt. Some thinkers instead turned to heat. In the 19th century, physicist James Clerk Maxwell proposed a thought experiment, now famous as Maxwell's demon. It imagined a tiny being controlling a door between two chambers of gas. The demon would allow only fast-moving molecules to pass one way and slow ones the other, seemingly creating a temperature difference and violating the second law of thermodynamics. Later refinements, like the Brownian ratchet, tried to achieve a similar effect using microscopic paddles moved by random thermal motion. But every version failed when examined closely. Maintaining the one-way motion always required more energy than the device produced, or random fluctuations negated the supposed gain. Nature refused to cheat. Others misinterpreted buoyancy. Some machines proposed using air bubbles or liquid pressure to create endless rising and falling motions. The concept sounds simple. Push air into a submerged chamber and let it float upward, driving a piston as it rises. Yet to push the air down in the first place demands the same amount of energy that is later recovered. The result, again, is balance, not surplus. Energy in equals energy out, minus what's lost to inefficiency. The broader idea of perpetual motion, a machine that runs forever without fuel, exists only in theory, within the boundaries of an isolated system. Such a system would need to be perfectly sealed, unaffected by outside forces, and immune to quantum fluctuations. In the real universe, that is impossible. Quantum uncertainty and environmental interaction ensure that no system remains truly closed. Thus, what people call perpetual motion usually refers to devices that appear self-sustaining for long periods but are secretly powered by small external energy sources. Take the drinking bird toy. Its hypnotic nodding seems endless, yet it relies on evaporation. As water evaporates from the bird's head, it cools the vapor inside, creating a pressure difference that dips the bird forward. When the water runs out, the motion stops. Similarly, capillary action pumps depend on tiny differences in pressure and temperature to lift fluids, but surface tension soon halts the process. Nature balances every equation. Even simple toys like the Crookes radiometer, a glass bulb with vanes that spin in light, demonstrate this principle. The motion comes not from the light pushing directly, but from temperature differences between the dark and bright sides of the vanes. Once those differences vanish, so does the motion. Solar-powered motors operating on the same principle can run for years under sunlight, but never exceed the energy they receive from it. Certain ingenious clocks, such as Cox's timepiece and the Beverly clock, harness slow environmental changes. They use fluctuations in air pressure or temperature to wend themselves, giving the illusion of infinite operation. In truth, they draw from a subtle, continuous energy source, the atmosphere itself. Likewise, the Atmos clock uses ethyl chloride gas, expanding and contracting with temperature shifts to keep its mechanism running. None of these devices defy physics, they merely exploit ambient variations. Some technologies achieve extraordinary longevity by tapping long-lived energy sources. Nuclear batteries powered by the decay of radioactive isotopes can run spacecraft for decades or even centuries. Flywheel systems, when placed in near-frictionless conditions, can store rotational energy for astonishingly long times. Space offers the ultimate testbed. Planets, moons, and asteroids spin freely for millions of years, gradually slowing as tidal forces bleed their energy into heat. Earth and its moon, for instance, exchange about 3¾ terawatts of energy each second through these subtle interactions. Even here, eternity remains out of reach. In the strange domain of quantum physics, phenomena like superfluidity and superconductivity seem to bend the rules. Superfluids flow without measurable friction, and superconductors allow electric currents to circulate indefinitely without resistance. Yet even these marvels are bound by balance. Once the system reaches thermal equilibrium or any disturbance occurs, motion ceases or energy is dissipated. The illusion of endlessness fades. Every attempt to break the laws of thermodynamics ends the same way. Equilibrium reasserts itself. Maxwell's demon may open its trapdoor, but the act of measuring, sorting, or maintaining that control consumes energy. The universe accounts for every transaction. Motion requires imbalance, and imbalance requires input. As long as energy conservation holds true, perpetual motion, beautiful in imagination, impossible in reality, remains one of humanity's most persistent dreams. However, deeper investigation revealed a fundamental truth. No matter how ingenious the design, any such mechanism would still increase the total entropy of the universe. In other words, it could not escape the second law of thermodynamics. The idea of a system that could extract useful work from random motion, known as the Brownian ratchet, was a captivating thought experiment. It imagined a tiny paddle wheel, jostled by the random collisions of molecules in a fluid, turning consistently in one direction, seemingly generating energy from chaos. But when scientists examined the idea on a molecular scale, they realized nature had already anticipated the trick. The same random motions that moved the paddle would also shake the ratchet itself. Heat fluctuations would erase any directional advantage, ensuring that the system could not produce net work. Entropy would always win. Zero-point energy emerged from quantum mechanics as another tantalizing concept. It refers to the faint hum of energy that remains even in what we call empty space. The vacuum itself never truly rests. The equations suggested that even when all motion stops, a residue of energy persists. Some visionaries and inventors have claimed this ocean of quantum energy could be tapped, powering civilization indefinitely. Yet every attempt to demonstrate this has failed under scrutiny. No reproducible method has ever shown that zero-point energy can do useful work. The consensus among physicists remains firm. Such devices defy known physics and belong more to pseudoscience than to possibility. The so-called ellipsoid paradox offered another case where physics appeared to defy logic. It described how radiation trapped inside a perfectly reflective cavity might behave strangely between two black bodies, seemingly leading to violations of thermodynamic equilibrium. But once the finite size of those bodies was accounted for, once the idealization was softened into physical reality, the paradox vanished. It was not the universe that had erred, but the assumptions of the thought experiment. Despite centuries of scientific progress, the allure of perpetual motion persists. Some believe machines capable of infinite energy already exist, hidden away by powerful interests. The narrative goes that governments and corporations suppress these technologies to protect fossil fuel industries and preserve economic control. Yet no credible evidence supports such claims. Every genuine test obeys the same immutable principles. Energy cannot be created from nothing, and disorder always increases. Fusion power, in contrast, does not attempt to defy physics but to master it. It seeks to reproduce, in controlled form, the same reaction that lights the stars. When two light atomic nuclei, typically forms of hydrogen, combine, they form a heavier nucleus and release tremendous energy. This is the process that keeps the sun burning, a natural fusion reactor sustained by gravity and heat. Since the 1940s, scientists have tried to bring this celestial process to Earth. The dream is simple: to harness fusion's near-limitless fuel supply and its clean, radiant energy. Yet, as of 2025, no experiment has produced more energy than it consumes. Fusion requires extraordinary conditions. The fuel, a plasma hotter than any material can withstand, must be confined long enough for atomic nuclei to collide and fuse. The required temperature hovers around 100 million Kelvin. To achieve this, scientists use magnetic fields or powerful laser pulses to trap and compress the plasma. The balance between temperature, pressure, and confinement time is known as the Lawson criterion, a mathematical gatekeeper that determines whether fusion can become self-sustaining. In the hearts of stars, gravity easily meets the Lawson criterion. On Earth, researchers use isotopes of hydrogen, deuterium, and tritium because they fuse more readily than ordinary hydrogen. When these two nuclei merge, they create a helium atom and a high-energy neutron. The reaction releases immense energy, but tritium is rare and unstable, with a half-life of roughly 12.5 years. To sustain fusion, engineers design lithium blankets around the reactor to breed tritium from neutron interactions, creating a closed fuel cycle. The advantages of fusion over fission, the process used in today's nuclear reactors, are striking. Fusion produces far less long-lived radioactive waste, poses no risk of meltdown, and uses fuel that cannot easily be weaponized. Yet challenges remain formidable. The neutrons generated in the reaction can erode reactor walls, damaging materials and reducing efficiency. Developing structures that can withstand such extremes is a major frontier of materials science. Two main approaches dominate fusion research. Magnetic confinement, developed in the mid-20th century, relies on powerful magnetic fields to trap plasma in a toroidal chamber. Early designs such as the Z-pinch and stellarator laid the groundwork, but it was the Soviet tokamak in the 1960s that proved most stable and efficient. In parallel, inertial confinement emerged in the 1970s, using laser pulses to compress tiny fuel pellets so rapidly that fusion occurs before the material can disperse. Today, the world's leading experiments, like the ITER tokamak in France and the National Ignition Facility in the United States, represent humanity's largest coordinated attempts to achieve controlled fusion. Private companies and smaller research groups now pursue alternative designs: magnetized target fusion, spherical tokamaks, compact stellarators, and even hybrid systems that merge magnetic and inertial techniques. The goal is not only to reach ignition, the point where fusion produces more energy than it consumes, but to do so reliably and affordably. Each design balances complexity, cost, and scalability in its own way. When physicists refer to a fusion reactor, they might mean either an experimental device or the hypothetical future power plants that could follow. A true reactor designed for electricity production would include systems to breed fuel, extract heat, and convert that heat into electricity using turbines or other engines. But at the core of every design lies the same physics. When two nuclei come close enough for the nuclear force to overcome their electrostatic repulsion, they fuse into one. The result is a small loss of mass converted directly into energy according to Einstein's equation, E equals mc squared. For lighter elements such as hydrogen, the process releases energy. For heavier ones, it requires it. This is why stars shine and why they eventually die. Fusion of hydrogen into helium powers them for billions of years, but once they reach iron, further fusion becomes energetically unfavorable. In a sense, fusion defines the life cycle of the cosmos itself, how matter transforms, how energy radiates, how order and entropy coexist. The pursuit of fusion energy on Earth mirrors this cosmic story, an effort to harness the same processes that shaped the universe, constrained not by imagination, but by the laws of physics. It is a challenge of patience, precision, and persistence. Though the dream remains unfulfilled, every new experiment brings humanity closer to understanding how the stars keep burning, and how one day we might do the same. And yet, hydrogen stands apart. Among all the elements, it is the simplest and the most cooperative when it comes to the extraordinary process of fusion. Because it possesses only one electron, hydrogen is easier to strip bare, its single electron easily detached when exposed to sufficient energy. Once ionized, what remains is a lone proton, a tiny nucleus that can join with others to release the power that drives the stars. But there is a problem. Even at microscopic scales, two positively charged nuclei repel one another. This electrostatic repulsion, known as the Coulomb barrier, keeps them apart. It is a force that grows stronger the closer the nuclei get, and overcoming it requires immense energy. Only when the particles are hurled toward each other with enough kinetic energy can they approach closely enough for the strong nuclear force, a force that operates only at subatomic distances, to take over. When it does, it binds them together, and fusion occurs. To achieve this on Earth, scientists must recreate the extreme conditions of stellar interiors. Atoms are heated until they no longer hold their electrons, forming plasma, a seething, luminous state of matter made of free nuclei and electrons. This plasma behaves unlike any ordinary gas. It can conduct electricity, generate magnetic fields, and respond dynamically to external magnetic forces. Because of this, magnetic confinement becomes the key technique for keeping the plasma in place. Machines like tokamaks and stellarators use carefully shaped magnetic fields to hold the plasma away from the reactor walls, preventing energy loss and damage to the structure. The challenge, however, is not simply to create plasma, but to sustain it long enough and dense enough for fusion reactions to occur efficiently. The energy generated must exceed the energy lost. This balance is captured in what scientists call the Lawson criterion, a benchmark that defines the conditions under which a fusion reaction becomes self-sustaining. It describes a delicate interplay between three quantities: plasma density, temperature, and confinement time. Their product, often referred to as the triple product, serves as a measure of how close a system is to break even, the point where power produced equals power consumed. In magnetic confinement systems, such as the ATIR project in France, the plasma density is low, about 1/10,000th that of air. To compensate for this near vacuum, researchers must either increase the temperature to hundreds of millions of degrees or extend the confinement time. As of the early 1970s, scientists succeeded in reaching fusion-relevant temperatures, but sustaining the plasma long enough has remained the core challenge. Magnetic fields can become unstable, and these instabilities can cause sudden losses of confinement. One strategy to reduce such losses is to build larger reactors. The bigger the device, the slower the rate of diffusion, and the longer energy remains trapped within. This explains why ITER is so massive. It is designed not merely as an experiment, but as a bridge towards sustained fusion energy. In contrast, inertial confinement fusion takes a different approach. Instead of magnetic fields, it relies on extreme compression. Tiny fuel pellets containing hydrogen isotopes are struck by powerful lasers or ion beams, squeezing them to densities over 100 times that of lead. Under such crushing conditions, the fuel's temperature rises so rapidly that fusion occurs in mere millionths of a second, just before the pellet explodes apart. At facilities like the National Ignition Facility, EF, in the United States, scientists have used this technique to reach and briefly surpass the threshold of ignition, demonstrating that fusion can indeed release more energy than the laser's input. The energy produced in fusion primarily emerges in the form of high-speed neutrons, especially in the deuterium-tritium reaction, the most efficient fusion process known. Because neutrons carry no charge, they slip easily through magnetic fields, striking the reactor's outer blanket. This blanket, often made of lithium, serves two critical purposes. It captures the neutrons, converting their kinetic energy into heat, and it breeds more tritium fuel through nuclear reactions with lithium atoms. The heat extracted from the blanket can then drive turbines, just as in conventional power plants, transforming fusion energy into electricity. Alternative designs aim to take this even further. Some propose hybrid systems that combine fusion and fission, using fusion-born neutrons to trigger reactions in nuclear waste, thereby generating additional power while reducing radioactive materials. Others explore advanced fuel cycles, such as proton-boron fusion, which produces energy mainly as charged particles instead of neutrons. This opens the door to direct energy conversion, systems that can capture the kinetic energy of charged particles and convert it straight into electricity without the need for steam turbines. Experiments conducted at the Lawrence Livermore National Laboratory in the 1980s demonstrated that such direct conversion could achieve efficiencies near 50%, an extraordinary figure for any energy process. Plasma itself remains a fascinating frontier. It is both fluid and electromagnetic, governed by the laws of magnetohydrodynamics. Within a fusion device, the plasma moves and twists, generating its own magnetic fields, shaping and sometimes destabilizing its confinement. In some cases, the plasma's motion expels external magnetic fields, a property known as diamagnetism. Magnetic mirrors can trap it, reflecting charged particles back and forth. These effects allow scientists to manipulate and control the plasma, though doing so at the required scales remains one of the most complex tasks in modern physics. The story of fusion is therefore one of persistence and precision, a quest to recreate the stars within the confines of human engineering. It demands mastery over heat, magnetism, and motion at a level no other technology requires. Each step forward, each improvement in confinement, temperature, or efficiency brings humanity closer to unlocking an almost limitless source of clean energy. The dream of fusion power is not a fantasy, it is a frontier, slowly yielding to decades of careful science and engineering, promising a future powered by the same forces that light the cosmos. And in the relentless search for clean, virtually limitless energy, humanity has turned to the stars for inspiration. Deep within every sun and star in the universe, the process of nuclear fusion transforms matter into light, heat, and life itself. On Earth, scientists are racing to replicate this same process in laboratories and massive experimental reactors, attempting to build an artificial sun, Among the many approaches devised over decades of research, one stands as the most studied and heavily funded: the tokamak. The tokamak concept was born in the Soviet Union in the late 1950s, and its name comes from a Russian acronym meaning toroidal chamber with magnetic coils. Its shape resembles a donut, technically a torus, within which a plasma hotter than the core of the sun is held in place by powerful magnetic fields. Inside that ring, an electrical current runs through the plasma, heating it and twisting it into stability. The goal: keep the plasma confined long enough, dense enough, and hot enough for atomic nuclei to fuse and release energy. The largest embodiment of this vision is the International Thermonuclear Experimental Reactor, or ITER, currently under construction in southern France. Once completed, it will become the largest tokamak ever built, a machine designed to prove that controlled fusion can produce more energy than it consumes. As of late 2018, more than 200 tokamak projects worldwide had been planned, decommissioned, or were still operating. Together, they represent decades of incremental progress toward harnessing a power source as old as the universe itself. Yet even within this single idea, innovation never stops. Engineers have developed a more compact version known as the spherical tokamak. Unlike the traditional donut, this design looks more like a cored apple, or a sphere pinched through the middle. Its smaller size allows for stronger magnetic fields relative to the plasma volume, potentially making fusion more efficient. Researchers call it a spherical torus. Experiments such as the UK's MAST upgrade and the US NSTXU have explored this design, seeking to maximize performance while reducing cost. But the tokamak is not alone. Another major branch of fusion research follows a different path: the stellarator. Instead of relying on electrical currents inside the plasma, the stellarator uses external magnetic coils shaped in complex, twisted loops to guide the plasma along a natural spiral. This reduces instabilities and allows for continuous operation without the pulsing required in tokamaks. The concept was pioneered by American physicist Lyman Spitzer in 1950, inspired by the desire to create a stable, steady-state fusion machine. Over time, the stellarator evolved into four main types: the torotron, helotron, heliac, and helus. Today, the most advanced stellarator in existence, the Wendelstein 7X in Germany, represents decades of precision engineering. Its magnetic field geometry is so intricate that each superconducting coil had to be fabricated with millimeter accuracy to maintain the plasma's shape. Beyond tokamaks and stellarators, other experimental concepts explore entirely different magnetic and inertial approaches. Some designs attempt to confine plasma using internal rings or conductors placed directly inside the hot medium. Early results showed that these rings quickly lost energy through conduction, making the method inefficient. However, advances such as the levitated dipole experiment revived interest by using superconducting coils that float magnetically in midair within the reactor chamber, reducing energy loss and mimicking the magnetic field structure of planetary magnetospheres. Another idea, the magnetic mirror, confines plasma along a straight magnetic field line by reflecting charged particles back and forth between magnetic mirrors at each end. This concept was developed in the 1960s by physicist Richard F. Post and his team. For 2 decades, the United States invested heavily in magnetic mirror projects, hoping to produce energy from this linear configuration. But by the 1980s, results suggested that mirror losses were too great, and funding shifted toward toroidal systems. Still, the concept lived on in the form of the bumpy torus, which arranged multiple magnetic mirrors around a ring to improve confinement. One of the best-known examples, the Elmo bumpy torus, operated at Oak Ridge National Laboratory during the 1970s and provided valuable insights into plasma behavior. Other experiments have explored self-organizing plasma structures, such as the field reverse configuration, FRC, and the spheromak. In an FRC, plasma generates its own internal magnetic field, forming a compact spinning structure that confines itself without the need for large external magnets. A spheromak works similarly but includes both toroidal and poloidal magnetic components, giving it greater stability. The dynamak concept, an evolution of the spheromak, maintains its plasma using a continuous magnetic drive. The University of Washington and startup companies such as Zap Energy have been developing these systems, aiming to commercialize compact, low-cost fusion reactors. Zap Energy's approach, known as the sheared flow stabilized Z-pinch, uses rapid flows of neutral gas to prevent the plasma column from breaking apart, a modern revival of an idea once thought too unstable to pursue. Meanwhile, other fusion methods rely not only on magnetic confinement, but on brute force, the compression of fuel using intense bursts of light. In inertial confinement fusion, lasers or particle beams squeeze a small pellet of deuterium and tritium until it reaches fusion conditions. Two main strategies exist: indirect and direct drive. In the indirect method, lasers heat a small gold cylinder, or hohlraum, which in turn emits X-rays that symmetrically compress the fuel. The largest facility employing this approach is the National Ignition Facility, NIF, in the United States, with France's laser megajoule following a similar design. In direct drive, the lasers strike the fuel pellet directly, as seen in experiments at the Laboratory for Laser Energetics and Japan's GECKO 12 system. A variant known as fast ignition uses a two-step process, first compressing the target, then igniting it with a second ultra-intense laser pulse. Although once promising, this method lost traction for large-scale energy production after 2019. Combining magnetic and inertial confinement led to hybrid techniques such as magneto-inertial fusion, where magnetic fields help stabilize plasma as it is rapidly compressed. The Z machine at Sandia National Laboratories is a prominent example, using immense electrical currents passed through fine tungsten wires to create X-rays that crush a fuel capsule. The principle resembles the older Z-pinch method, which channels current through plasma itself, producing inward magnetic pressure. While early machines like the UK's Zeta in the 1950s showed initial signs of fusion, the approach struggled with stability limits. A related variant, the theta pinch, drives current around the outside of the plasma instead of through it. Early experiments such as the Scylla device achieved fusion, but failed to maintain the conditions needed for power generation. Over the decades, researchers have explored nearly every possible configuration. The screw pinch combined elements of both theta and Z pinches, aiming for better stability. The Polywell attempted to merge magnetic confinement with electrostatic forces, reducing energy loss within the magnetic cage. Magnetized target fusion sought to compress magnetically trapped plasma using mechanical or inertial pressure. Companies like General Fusion in Canada are pursuing versions of this, using spinning liquid metal walls and synchronized pistons to compress plasma spheres, while others, like Hyperjet Fusion, use colliding plasma jets to create a high-pressure plasma liner. There have even been unconventional and exotic ideas. Muon-catalyzed fusion replaces electrons with much heavier muons, allowing hydrogen nuclei to come close enough to fuse at relatively low temperatures. Although experimentally verified, this method consumes more energy to produce muons than it releases in fusion reactions. Another proposal, lattice confinement fusion, uses metal lattices, often saturated with deuterium, exposed to radiation or ion beams. The lattice structure helps bring atomic nuclei together without the need for extreme plasma temperatures. While not producing net energy, such research continues to probe the boundaries of nuclear physics and materials science. At the other end of the spectrum lies the fuser, a deceptively simple device consisting of two spherical grids inside a vacuum chamber. A strong electric field accelerates ions toward the center, where they collide and fuse. Despite heavy energy losses, amateur scientists and students around the world have built small fusers capable of achieving measurable fusion reactions, a testament to the accessibility of this branch of physics. And finally, colliding beam fusion explores what happens when high-energy particles are accelerated and smashed into one another. Though primarily used for research in the 1970s and 1980s to study reaction cross-sections rather than power generation, it remains an important part of understanding the physics of fusion at the most fundamental level. Across all these methods, magnetic, inertial, hybrid, and exotic, the challenge remains the same. Every known fusion system still consumes more energy than it produces. Yet, each experiment, each iteration, and each failed design adds to a growing body of knowledge that brings humanity closer to the long-sought goal of sustainable fusion power. The quest continues, not just as an engineering project, but as a story of scientific endurance, creativity, and the human will to capture the power of the stars. However, it is not a practical path for sustainable power generation. The fundamental obstacle lies in the immense energy required to maintain and focus the beams, energy that far exceeds what is released by the fusion reactions themselves. The challenge of harnessing fusion is therefore not the reaction itself, but the art of control. In recent years, researchers have turned to artificial intelligence, specifically deep reinforcement learning, to address this challenge. Inside a tokamak, a donut-shaped chamber where hydrogen plasma swirls under intense magnetic fields, AI systems now learn to stabilize the plasma in real time. These systems continuously adjust magnetic coils, discovering through trial and error the most efficient way to confine and heat the volatile plasma. Each millisecond counts, and every movement of the magnetic field is a calculated act of balance. In 2014, Google partnered with TAE Technologies to explore how machine learning could predict plasma behavior and help control the Joint European Torus, one of the world's largest operating fusion reactors. Later, DeepMind, another branch of Google's AI ventures, developed a reinforcement learning system capable of controlling plasma configurations in variable-shaped tokamaks. This represented a shift from rigid, pre-programmed control toward adaptive, intelligent systems that learn the dynamic language of fusion. Meanwhile, researchers continue to refine the methods used to heat and maintain plasma. Electrostatic heating employs electric fields to accelerate charged particles, ions, and electrons, raising their energy until the gas transforms into plasma. Neutral beam injection takes a more direct approach. Hydrogen atoms are first ionized, accelerated into a high-energy beam, then reneutralized before being fired into the reactor. When this beam collides with the plasma, it transfers energy, heating and refueling it simultaneously. Any residual charged particles are safely redirected to cooling systems. Radio frequency heating works in principle much like a microwave oven. Powerful radio waves are tuned to resonate with the motion of electrons in the plasma, a process called electron-cyclotron resonance heating. Specialized devices called gyrotrons generate these high-frequency waves, efficiently transferring energy into the plasma core. As the plasma evolves, another phenomenon comes into play: magnetic reconnection. Here, the tangled magnetic field lines within the plasma snap and realign, unleashing bursts of stored magnetic energy. Up to 45% of this energy can be converted directly into heat, further fueling fusion reactions. In some designs, magnetic oscillations, alternating currents pass through magnetic coils, create rhythmic waves of heating, helping sustain the plasma's temperature and stability. On the theoretical frontier lies antiproton annihilation. Injecting antiprotons into fusion fuel could theoretically trigger thermonuclear reactions, releasing tremendous amounts of energy. Though far from practical, this concept was studied as part of the AIM-STAR project at Pennsylvania State University, exploring the use of antimatter as a catalyst for deep space propulsion. Diagnostics remain the hidden backbone of fusion research. Every flicker of plasma, every particle emitted must be measured and analyzed. In commercial fusion plants of the future, monitoring systems will likely be more streamlined than those in today's experimental reactors, yet they must endure harsher conditions: higher plasma temperatures, stronger neutron radiation, and complex tritium breeding cycles. Advanced sensors will be required to separate helium and impurities, track tritium within lithium blankets, and ensure safe and continuous operation. Among the diagnostic tools, the flux loop is a fundamental instrument. By placing a loop of wire within the magnetic field, scientists measure the induced current to calculate the total magnetic flux passing through the loop. This method has been essential in experiments such as the National Compact Stellarator experiment, the Polywell, and the levitated dipole experiment. Another indispensable device is the Langmuir probe, a small metal tip inserted into the plasma. By applying a controlled voltage, the probe collects charged particles and generates a current that changes with voltage. Plotting this as an IV curve reveals vital plasma characteristics, including local density, potential, and temperature. Thomson scattering provides another window into plasma behavior. By observing how light scatters from electrons in the plasma, researchers can determine both its temperature and density. This technique is widely used in inertial confinement fusion, ICF systems, where lasers or particle beams compress tiny fuel pellets to extreme conditions. In such systems, additional beams may be fired into gold foils to generate X-rays that pass through and illuminate the plasma, allowing precise optical measurements. Neutron detectors serve as the primary tools for measuring fusion output. Each neutron emitted represents a successful fusion event, and by tracking their rate and distribution, scientists gain insight into the reaction's intensity and stability. X-ray detectors complement these measurements, capturing radiation emitted when charged particles are deflected by magnetic fields or collide with one another. Depending on speed and energy, this radiation appears as cyclotron, synchrotron, or bremsstrahlung emissions, each offering clues about plasma dynamics. Surrounding the reactor, neutron blankets absorb the flood of high-energy neutrons produced by fusion. As these blankets capture neutrons, they heat up, and the energy can be harvested to generate electricity, usually by converting it into steam that drives turbines. Moreover, breeder blankets made from lithium-based materials can produce new tritium fuel, ensuring a self-sustaining fusion cycle. These systems may take the form of liquid lithium walls or helium-cooled pebble beds composed of lithium ceramics. Some researchers envision bypassing the traditional steam cycle entirely through direct conversion. This process transforms the kinetic energy of charged fusion products directly into electricity. Proposed by physicist Richard F. Post in the late 1960s, it involves guiding charged particles through electric fields so that their motion induces usable current. Experiments have demonstrated efficiencies as high as 48%, showing promise for future compact fusion systems. A related technique involving traveling wave tubes channels high-energy helium nuclei through coiled wires. As the particles move through at millions of electron volts, they induce electric currents that can be harvested for power, an elegant intersection of plasma physics and electrical engineering. At the core of all these approaches lies one principle: confinement. To sustain fusion, plasma must remain both hot and dense long enough for the atomic nuclei to collide and fuse. Achieving equilibrium, where all forces acting on the plasma are balanced, is the central challenge. Too little confinement and the plasma cools. Too much instability and it escapes. Every innovation in fusion technology, from magnetic coils to machine learning systems, aims to perfect this delicate equilibrium, the balance between chaos and control that defines the dream of harnessing the power of the stars. However, in the realm of inertial confinement fusion, every microsecond counts. The plasma, a chaotic, searing state of matter composed of charged particles, must fuse before it has a chance to fly apart. In this brief window, unimaginable forces converge. If the plasma disperses too quickly, the opportunity for fusion is lost. Stability is therefore essential. A stable plasma holds its shape against the push and pull of turbulence. Even the smallest disturbance, a ripple in density or temperature, can spell the end of a reaction that took months to prepare. Equally critical is controlling transport and conduction. The plasma must not lose material or energy faster than it can sustain the reaction. When charged particles drift away or when heat escapes through conduction into the surrounding structure, the fusion process falters. To achieve what scientists call self-sustaining fusion, part of the energy produced must flow back into heating the fuel itself, an elegant loop of creation feeding on creation. Only when the plasma gives back as much as it receives does true ignition begin. One of the earliest tools designed to harness such behavior was the magnetic mirror effect. In this phenomenon, a charged particle moving along a magnetic field line approaches a region of stronger magnetic intensity. As it nears that boundary, the growing field acts like an invisible wall, reflecting the particle back along its path. During the 1960s through the 1980s, researchers at Lawrence Livermore National Laboratory built several fusion machines based on this idea, so-called magnetic mirror devices. Similar principles appeared in configurations like magnetic bottles and biconic cusps. The mirror approach had attractive features. It was simpler to construct and maintain than ring-shaped reactors and made direct conversion of energy more feasible. Yet the simplicity came with a price. Confinement proved weak and particles escaped too readily. Gradually, most mirror programs were abandoned, except for experimental successors such as the Polywell, which sought to revive the concept in modern form. To improve confinement, engineers learned to bend magnetic fields into loops. These magnetic loops form circular or toroidal surfaces that trap plasma more effectively. Among the best-known devices employing these geometries are the tokamak, the stellarator, and the reversed field pinch. Compact configurations like the field reverse configuration and the spheromak aim to keep the advantages of toroidal surfaces while reducing mechanical complexity. Their designs differ from the perfect ring shape, allowing flexibility in how plasma stability and field strength are balanced. Each represents a unique experiment in taming nature's most energetic state. In contrast to magnetic confinement, inertial confinement takes a radically different path. Instead of holding the plasma in place with magnetic fields, it crushes the fuel inwards so quickly that fusion occurs before the material can escape. The process begins with a tiny fuel pellet, usually containing deuterium and tritium, encased in a thin shell. In an instant, powerful energy sources such as lasers, ion beams, or X-rays bombard the pellet from all sides. The outer layer vaporizes, and the recoil forces drive the inner layers inward, compressing the core to nearly 30 times its normal density. In this extreme compression, the temperature soars to millions of degrees, and fusion ignites. Two primary strategies exist: direct drive, where lasers strike the target directly, and indirect drive, where the beams first heat a surrounding enclosure, which emits X-rays that uniformly compress the fuel. Though lasers are the dominant choice, experiments have also explored heavy ion and electron beams for the same task. The challenge lies in achieving perfect symmetry. Even slight unevenness can cause the implosion to fail. Another intriguing path is electrostatic confinement, in which electric fields, not magnets or lasers, accelerate ions toward each other. The fusor is the classic example. It consists of a spherical anode cage surrounding a smaller cathode. Positive ions are drawn inward toward the negative core, gaining energy as they move. Occasionally, two ions collide with enough speed to fuse. However, many strike the inner cage instead, wasting energy as heat. Radiation and conduction further sap efficiency, leading to low fusion rates. To overcome these flaws, researchers proposed variants such as the magnetically shielded grid, the plasma oscillation device, the penning trap, and the polywell. Each seeks to maintain an electrostatic field without a physical grid that absorbs energy, but none has yet achieved practical fusion power. At the heart of all fusion systems lies the choice of fuel. The leading candidates are isotopes of hydrogen, deuterium and tritium. Deuterium is plentiful, found in seawater and semi-heavy water, and can be extracted with relatively low effort. In contrast, tritium is rare. With a half-life of only 12 years, it decays quickly and must be produced artificially. Fusion reactors therefore plan to generate it within breeding blankets made of lithium. When bombarded by high-energy neutrons from the fusion core, lithium nuclei react to form tritium, creating a closed fuel cycle. Helium-3, another potential fuel, captures scientific imagination because it produces little neutron radiation. Yet helium-3 is scarce on Earth. To obtain it in quantity would require mining extraterrestrial sources such as the Moon, or producing it through other nuclear reactions. Similarly, advanced proposals involving proton-boron 11 promise clean, low-radiation fusion, but demand extreme temperatures far beyond today's capabilities. The deuterium-tritium DT reaction remains the most studied and most energetic of all fusion processes. In DT fusion, nearly 80% of the released energy emerges as high-speed neutrons. These neutrons are both a blessing and a curse. They carry energy that can be converted to heat for electricity generation, but they also bombard reactor materials, like making them radioactive over time. The intense neutron flux, estimated to be about 100 times higher than in traditional fission reactors, poses severe challenges for materials science. Metals weaken, ceramics crack, and reactor walls must be replaced periodically. Tritium leakage presents another concern. As a radioactive gas, it can escape through microscopic cracks or permeate containment structures, raising environmental and safety issues. After major deuterium-tritium experiments, such as those conducted at the Joint European Torus, the reactor's vacuum vessel became so radioactive that robotic systems were required for maintenance for over a year. Inside a working reactor, the neutron energy must be harnessed efficiently. The lithium breeding blanket serves two critical functions, generating new tritium and capturing neutron energy as heat. This heat drives turbines or other energy conversion systems. In advanced designs such as the lithium tokamak experiment, lithium is placed directly in contact with the plasma core. There, it helps control recycling, an effect in which escaped hydrogen re-enters the plasma and destabilizes it. These experiments demonstrate that liquid lithium not only sustains reactions but also protects the reactor structure. Deuterium-deuterium (DD) fusion offers another pathway. Two deuterium nuclei can fuse in two equally likely ways, one producing tritium and the other producing helium-3. Though the process does not require external tritium or lithium, it inevitably generates some tritium internally. Operating at around 15,000 electron volts, slightly higher than DT fusion, it is cleaner but less energetic. If managed carefully, the tritium produced can be burned within the same system, reducing external handling and minimizing radioactive risks. Step by step, across decades of research, these methods reveal a story of persistence. Magnetic mirrors, toroidal loops, imploding pellets, electrostatic grids, all are milestones on the path to a goal humanity has pursued for over half a century, to capture the power of the stars. Each approach illuminates a different facet of the same dream. A controlled fire that burns without end, fueled by water, guided by magnets, and sustained by the same forces that light the sun. However, this results in the birth of even more neutrons, particles that now carry greater energy and far more destructive potential. In the deuterium-deuterium, or DD reaction, each neutron emerges with about 2.5 million electron volts of energy, roughly 4/10 of a picojoule. But when deuterium fuses with tritium, the energy jumps to over 14 million electron volts, equal to a little more than 2 picojoules per neutron. That difference may seem small, but it profoundly alters how fusion behaves. With more energetic neutrons, the surrounding materials in a reactor face accelerated wear and complex transmutation processes that create new isotopes. If scientists remove the tritium quickly and replace it with helium-3, they establish what is known as a tritium-suppressed fuel cycle. The discarded tritium naturally decays into helium-3 over 12.5 years, and by reintroducing that helium-3 into the plasma, the reactor can continue operating without depending on structures designed to resist high-energy neutron damage. In theory, if all the tritium were consumed during operation, the total energy carried away by neutrons would fall by roughly 18%. The DD fuel cycle holds appeal because it eliminates the need to breed tritium from lithium. It also reduces dependence on rare lithium resources and produces a gentler neutron environment. Yet these benefits come with trade-offs. The plasma must confine energy for about 30 times longer than in the deuterium-tritium, or DT reaction, and at the same pressure and volume, the DD process produces about 68 times less power. In the purest form of DD fusion, where tritium is fully removed and helium-3 is continuously recycled, only about 6% of the released energy escapes as neutrons. This version of tritium-suppressed fusion is far less damaging to materials, but it demands plasma conditions that are even more extreme. Energy confinement must be 10 times longer than in the DT process, and temperatures must reach roughly twice as high. Another avenue for fusion energy lies in helium-3 reactions. When helium-3 nuclei fuse, they yield helium-4 and a single high-energy proton. Like proton-boron fusion, most of the resulting energy emerges as charged particles rather than neutrons. This makes it possible to capture energy more efficiently through direct conversion instead of using traditional heat cycles. It also reduces the radioactivation of reactor components, a major advantage for maintenance and safety. Yet, despite these advantages, DD reactions inevitably still generate many neutrons, pushing researchers to consider proton-boron fusion as the leading candidate for so-called aneutronic fusion, fusion that avoids producing neutrons almost entirely. In such a process, the lack of neutrons also reduces concerns about radioactive waste and proliferation, since the materials do not become highly activated. Among known reactions, helium-3 fusion is theoretically the most reactive aneutronic option. However, acquiring sufficient helium-3 presents a monumental challenge. On Earth, the isotope is exceedingly scarce, so proposals involve mining it from the lunar surface or collecting it from the outer atmospheres of giant planets like Uranus or Saturn. These prospects remain technologically and economically prohibitive. As a result, many researchers see proton-boron fusion, combining the most common form of hydrogen, called protium, with boron, as the most feasible aneutron pathway. When hydrogen and boron fuse, they form energetic alpha particles, helium nuclei, that can have their kinetic energy directly converted into electricity without intermediate steam turbines. Only a very small fraction of side reactions produce neutrons, carrying less than 0.1% of the total energy. This dramatically reduces radiation hazards and the gradual structural weakening of reactor walls. The optimal temperature for this reaction is around 123,000 electron volts, about 10 times higher than the requirement for deuterium-tritium fusion. The confinement challenge, however, is immense. Energy must remain trapped 500 times more effectively than in DT fusion, and the power density, the energy produced per unit volume, is about 2,500 times lower. Even so, per unit mass of fuel, proton-boron fusion can deliver more energy than conventional nuclear fission. Conventional magnetic confinement systems like tokamaks and laser-driven inertial confinement systems are poorly suited to the extreme precision and stability required for aneutronic reactions. Therefore, alternative devices are under investigation, including the polywell and dense plasma focus systems. These configurations attempt to use electrostatic or magnetically pinched plasmas to achieve the intense, short-lived conditions necessary for clean fusion. In 2013, a research team led by Christine Lebon at the École Polytechnique in France achieved a significant milestone. During a laser pulse lasting only 1.5 nanoseconds, they recorded an estimated 80 million proton-boron fusion events, about 100 times more than any previous attempt. The experiment offered proof that with sufficient focus and power, the once theoretical dream of aneutronic fusion might be experimentally attainable. Material science remains one of the major bottlenecks for any type of fusion reactor. Inside these machines, structural components must endure both extreme temperatures and constant bombardment by high-energy particles. Plasma wall interactions can erode surfaces, release trapped gases, and change the very chemistry of the materials. Neutron damage, in particular, can displace atoms within the crystal lattice, creating brittleness and radiation-induced swelling. To manage hydrogen recycling and control tritium inventories, materials with low hydrogen permeability are essential. Pure metals like tungsten and beryllium, as well as compounds such as carbides, dense oxides, and nitrides, are prime candidates because they resist both hydrogen absorption and diffusion. Yet how these materials are processed often determines their success. Surface engineering plays a vital role. Techniques such as controlled oxidation can create thin, stable layers that block hydrogen penetration. Other strategies use reactive gas atmospheres, magnetic fields, or electric potentials to alter surface properties dynamically during reactor operation. Evaluating these protective barriers remains difficult, and one of the most reliable tests continues to be the classical permeability method, measuring how much gas passes through a coated membrane under controlled pressure and temperature. This combination of plasma physics, nuclear engineering, and materials science forms the foundation of humanity's ongoing attempt to replicate the sun's power here on Earth. Each approach, whether DD, DT, helium-3, or proton-boron fusion, carries its own balance of practicality, efficiency, and purity. The challenge is not in making fusion happen, but in making it happen reliably, economically, and cleanly.